Afternoon, sir. Yes.
Yeah, okay. So in this session, we'll be revising the week 9 to 12. Okay, so but first we'll be discussing the week 10. Okay, week 10 I'll be
So
doing
your
the,
voice is very low.
okay. I'll try to amplify my voice. So first we'll discuss week 10. Okay, and after that 9, 11, and 12 we shall be covering. Okay.
So not
First,
able to hear you.
you're not able to hear me at all.
Very low. I guess it's
I think
fine.
it's his network, sir.
Yeah, it's fine, I guess. Ram.
It's fine.
Yes,
Yeah.
yes.
Yes, sir.
Okay, so first we'll discuss week 10, okay? And after that, Mr. Vishal will be discussing the 9, 11, and 12, okay? So,
Excuse
let
me, sir.
Yeah,
Sir, before starting to week 10 content, I would like to ask some few questions regarding the practice assignment 11. So, can I ask them?
practice assignment 11, right? Week 11?
Yes, sir.
Yeah, that you could ask later because I have this one more session that I need to be joining it for Python. So, we are on tight schedule, like I'm on tight schedule. So, first we'll discuss week 10, okay?
Okay,
Yeah,
sir.
after that, I'll discuss the questions, practice assignments. Okay.
Okay, sir. Thank you.
Okay, thanks. Okay. So we look at the properties of convex functions, okay? Like for the convex functions, right? All the local minima are going to the global minima. That is one thing, okay? And wherever we are having this global minima, right? Obviously, we should be having at that particular point gradient of f of x star that should be equal to 0, okay? And the like this is just a proof for that. And the other important one is that wherever we have this like whenever we have two functions f of x and g of x which are convex, then the sum of those two functions is again going to be the convex of it, okay? The proof for that was mentioned here, but we'll not be getting into that, okay? But whenever we have f of x is convex and g of x is convex, okay, two different convex functions, then the sum of those two functions will again be a convex function, okay? Then now coming to the compositions, that is f of g of x kind of one, where f is convex and g is convex. It's not always that f of g of x will be convex, okay? But under certain conditions, it is going to be a convex function, okay? For example, here, when we have here f is a convex and non-decreasing function and g is a convex function, then we'll have f of g of x is a convex function, okay? Later, when we have this f, when you have g as a linear function, okay, and f is a convex function, then this f of g of x is going to be a convex function. All right. So under these two conditions, we can have this. I mean, where f is a convex and non-decreasing, and g is a convex, then f of g of x is going to be a convex function. And in the second scenario where g is a linear function and f is a convex function, there we have this f of g of x as a convex function. Okay. In general, it's not always true that f of g of x
Can
is
I
going
explain
to
the
be convex.
two conditions, sir, F and G again?
Can you repeat?
Can I explain the F and G conditions again? The convex linear.
Okay. So we have here, let's say f is a convex function and it is a non-decreasing function. Okay. And it should be a non-decreasing function, and g is a convex function. Then we have this f of g of x is a convex function. Okay. F should be convex as well as non-decreasing. Okay. You know what is meant by this non-decreasing function, right?
Yes, sir. Yes, sir. Right.
Yeah. So in that particular scenario, we have this f of g of x will be a convex function. Okay. The composition of it, h of x is f of g of x will be a convex function. That is the first scenario. And in the second scenario, we have f is a convex function and g is a linear function. Okay. If g is a linear function, then we can say that f of g of x is a convex function. Okay. Clear?
Yes, sir. Clear.
Okay. But in general, it's not always true that when f and g both are convex, f of g of x need not be convex. Okay, clear? Okay. Now coming to this part, like we could be using this optimization part to apply for linear regression. Okay, what happens is for the linear regression model, right? We assume that the parameter, the y value, right? Okay, y value depends on this x values. Okay, some input values. Okay, which is of d dimensions, and it is of linear model. That is this y is going to be equal to w1 x1 plus w2 x2 plus w3 x3 and so on wn xn, where is w1 w2 w3 those are called as this weight. Okay, weight vector. Okay, that all the w's combined, it's called as the weight vector. Okay, so in general we'll assume this y equals to h of x is w transpose x. Okay, this is a linear model. Okay, so for us to get the best model, right? So the only thing which we could vary is this weighted vector. Okay, this weighted vector we could be varying. And how do we get the best weighted vector? Okay, whichever ones gives you the least error, this w transpose x is the one which you are predicting it, and yi is the actual value, and the difference between the predicted value and the actual value, right? I mean the squared error, this is called the difference between the predicted value and the actual value, that is called as the error. And then the squared error value, we should be minimizing it. The sum of the squared errors, if we are able to minimize it, then we can find the optimized w vector. Okay, so which will actually be the solution for the linear regression model. Okay, so here you could see we have here w transpose xi minus yi whole square, right? This is a, I mean basically we should be minimizing this. Okay, this we know that w transpose minus xi, w transpose xi minus yi, this is a linear function, right? Okay, and w transpose xi minus yi whole square, this is similar to f of x square. Okay, z square one. Okay, and we know that we know that x square is a convex function, so we have here w transpose xi minus yi whole square. Okay, that is a convex function. So for us to minimize it, we could be solving it using the normal gradient descent method. Okay, using the normal gradient descent, we can be solving for this. Okay, so we have here f of w equals to the sum of the vectors. Okay, I mean the sum of the squared errors, and this we could be representing it this form, like w transpose xi minus yi. If you take that as this vector, okay, w transpose xi minus yi whole square, sum of that is nothing but the length of that particular vector. Okay, and we know the length of that particular vector is nothing but xw minus yi transpose. I mean length of any vector is nothing but x transpose x, right? So similarly we'll be doing that, so which gives us f of w equals to xw minus y transpose of xw minus y. Okay, this half value we have added. Okay, we'll mention the reason for why we added half. Basically, if you are reducing the squared error, right? If you want to minimize the squared error, it is same as minimizing half of the squared error. Okay, it's going to be the similar one. Okay, now if you do the gradient of it, you'll be getting this value, which is x transpose xw minus x transpose y. Okay, for us to get the optimized value, right, when it is a convex function, when will you get the global minimum? That is when gradient of f of w is going to be 0, right? When you equate it to 0, okay, when you equate it to 0, you'll be getting w as x transpose y multiplied by x transpose x inverse. Okay, x transpose x inverse multiplied by x transpose y. But this is the actual analytical solution. Okay, but doing this inverse, it's not always going to be easy. So instead of doing the analytical one, what you will be using is we'll be using the gradient descent method. Okay, to get the solution. So what is this gradient descent method? Which we know this iterative process, right? we assume this WT plus 1 equals to WT minus step size eta t gradient of f. Okay, so this gradient of f can be easily computable. So x transpose x w minus x transpose y, and WT is a weighted vector at the tth iteration. Okay, so using the iterative process, we can be easily solving for the optimized. I mean, we can easily get the optimized weighted vector W. Okay, so here we assume that x transpose x inverse exists. Yeah, like for us to solve it using the gradient descent method, we need not assume that x transpose x inverse exists actually. Okay, so that is one of the cases where the analytical solution works. Only for the analytical solution, you need the x transpose x inverse. But for the gradient descent iterative process, right? You need not get the x transpose x inverse. So it doesn't matter whether the x transpose x inverse exists or not. Okay.
So the gradient will keep changing, right, after every iteration?
Yeah, the gradient will keep changing because the W will change. Yeah. We need to be stopping. I mean, when will you get the solution for gradient descent? When gradient of f of W is going to be 0, right? That's when you will stop the gradient descent algorithm, or approximately 0. Okay. So ultimately that's our goal. Okay. To make the gradient as 0, but then we won't be solving for it directly using this analytical solution, but we'll be doing it step by step. Okay. So when will you stop? You will stop when WT plus 1 equals to WT, right? That happens when this gradient is 0. Okay. So this is one important one, like based on the, I mean, given the weighted vector and then the x and y, right? X vectors on x matrix and then the y vector, you should be able to find out the WT plus 1. Okay. Using this gradient descent method, we won't be asking you to solve for the analytical solution. Okay. Analytical solution we won't be asking you to do because finding the inverse, it's not going to be easy, but we'll just be asking you for the t plus 1 iteration. Like given a W vector, we will ask you to find the next W vector from that. Okay. Given W1, we will be asking you to find W2. Okay. Is this clear?
Yes, sir.
Okay.
Yes, sir.
So the next part is this constraint optimization part. Okay. We won't be asking, I mean, we won't be getting too much into this KKT conditions part, but then given a conditions, you should be knowing how to maximize or minimize it. Okay.
So KKT conditions will not come.
No, KKT conditions will not become. Okay, but we'll still be asking you to find out the maximum value given a smaller condition. I mean, like given some conditions, we will still be asking you to find the maximum value. Okay, clear?
Sir, so there we will use Lagrangian method, right?
Yeah.
Sir, can you please explain with an example?
With an example of like the problem, like this one, the maximization part with respect to some constraints.
Yes, sir.
That one?
Yes, sir.
Sir, also in that gradient descent, range is not there, sir. Numeric value type answer is given in the mock test. So
And
even
like-
if there is one decimal difference, our answer is coming out to be wrong, sir.
Correct. So, but in the actual test, what's going to happen is we are going to ask for a range. Okay, we'll be asking you to enter a value up to like two decimal places. Okay, and then even for those 2 decimal places, we'll give you a range. It won't be a single value. Okay, it's going to be a range. Okay, so you don't have to worry about that. Clear?
Yes, sir.
And sir, you were mentioning that in constraint optimization, we have only Lagrangian method and there won't be anything from that KKD.
Yeah.
Okay, thank you, sir.
Okay. But actually, if you look at it, the way to solve for this Lagrangian is with respect to the condition is using the KKT. But what I was trying to say is that we won't be asking you to find out that U1 value, U2 values, all those you won't be asking. But in general, we'll just be asking you to, like, for example, let's say given you know this x square plus y square one. Okay, given x square plus y square equals some value, and then we will ask you to find the maximum value of xy. Okay, so that you could directly solve it using the analytical one. Okay, let me just show you the example for it. So here xy, we want to maximize xy. Okay, maximize xy, and then like the condition could be something like x cube plus y cube equals to 1. Okay, x cube plus y cube equals to 1, or let's say something like sine of xy equals to 1. Okay, anything could be there. Okay, so what you should be doing is, instead of this in the xy part, you should either be replacing. So this you could write y cube in terms of x cube, right? You write y cube equals to 1 minus x cube. Okay, y cube equals to 1 minus x cube, which gives you y equals to 1 minus x cube power 1 by 3. Okay, is this clear? This one? Okay.
Yes, sir.
Cube root of 1 minus x cube. Okay, so we'll just substitute this value here. So what we need to maximize is, I mean, our f of x, it won't be f of x comma y, because okay, initially f of x comma y is going to be equal to xy. Okay, this you could rewrite it as xy equals to x into, we'll substitute the y value here, 1 minus x cube power 1 by 3. Okay, these are f of x. Okay, now since it is of just of like one variable, I have written in this form. So for you to maximize it, you know, right, we just need to be differentiating it, okay, with respect to x, and then like equating it to 0. If you do that, and then if you solve for it, then you'll be finding the maximum value. Okay, is this clear what I'm talking about?
Yes, sir.
Yeah, this alone, if you're able to do, then that's good enough. Okay.
Sir, should we equate 0 to first differentiation, sir?
Yeah, correct. Because only then you'll be able to find either minimum or maximum. Okay.
But this same problem we can do with the Lagrange also, right?
Yeah, you could solve it using the Lagrangian too. Okay. I'm not saying that you cannot solve it using the Lagrangian one. Okay, that's why I told that whenever you're having the objective function and then a constraint, right? So you can actually solve it using the Lagrangian one. Okay.
Yeah.
But then solving it.
The answers to both approaches will be same, right?
Yeah. Obviously, they should be same. Yes. Okay.
But sir, if we find two positive values, so which one is maxima?
If you find two maximum values, that's what you're saying?
Yes, sir. So which value is greater than it is maximum?
Okay, let's say like you found different x comma y values. Okay, different x comma y values for which, okay, whatever equation I given, right, this f dash of x1. Okay, we have this f of x equals to x into x minus 1 minus x cube power 1 by 3, right? So let's say you had done f dash of x equals 0, okay, and then you solve for it. You got two different x values. Okay, you got two different x values as an answer. Okay, as a solution for f dash of x equals 0. Okay, you should be, there are like two things you could do. Okay, one you could directly substitute. You could directly find the corresponding y value and then substitute here in xy. Okay, you'll find xy value for the first pair and xy value for the second pair. Whichever is the maximum, that's a solution. Okay, whichever is the maximum, that's a solution.
Okay,
Clear?
sir. Okay.
That is like one way, and then the other way is you could go for this f double dash of x, okay, f double dash of x. So for one it could be like f double dash of x could be less than 0, and for the other it could be like f double dash of x greater than 0, okay. For you to get the maximum value, f dash of x should be equal to 0 and f double dash of x should be less than 0, okay. Then only you'll be able to maximize the function. For minimization it's opposite, okay. F dash of x will be equal to 0, but f double dash of x will be greater than 0, okay. Clear what I'm talking about?
Yes, sir.
So if f double dash of x greater than 0, it's max minimum.
No, if f double dash of x is greater than 0, then you'll be getting the minimum at that particular point.
Getting
Right.
what?
Let me just show you this. I'll take an example and then I'll show you. Let's say f of x equals to x square. Okay. What is f dash of x? F dash of x is 2x, right? Correct?
Yes.
F dash of x. I'll mention it as like f1 of x. Okay. f1 of x is 2x. Okay. And then you equate it to 0, you'll get x as 0. Okay. Which will give you x as 0. Okay. And then you do the f double dash of x. F double dash of x at this particular for 2x is it's going to be 2, right?
Yes.
Correct. So and then we have this f double dash of x is positive. 2 is positive, right? 2 is like greater than 0. So at x equals 0, you'll be getting minimum. So the minimum value that is possible for the x square function is x equals 0. But that we already know, right? X square is always going to be positive. The least value that is going to be that's possible for x square is going to be 0. Okay. But let's say I have this f of x equals to minus x square. Okay. Minus x square. Now you do for this f1 of x, you'll get minus 2x, equate it to 0, you'll get x as 0. And then you do f double dash of x, you'll get minus 2 as the answer. Okay. Since f dash of x is 0 and then f double dash of x is like less than 0, at x equals 0, you'll have maximum. All right. Am I making sense?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir. This part is clear.
Yeah. So if you're able to find that part alone, then that's good enough. Okay. So we'll not be asking questions with respect to the Lagrangian one. Okay. So we did not discuss about it. Okay. Even theory questions we will not be asking. So it's okay if you do not entirely understand the KKT conditions. All right.
But
Yeah.
sir, the problem which you showed earlier, can that be solved using lambda that is del f equals to lambda del g? That can that be solved with
Like
that method?
you were saying the KKT conditions, using the KKT conditions, can you solve? That's what you're asking?
No, sir. Actually, there was some concept right in the week 9, I think.
Okay, the week 9, which was that Mr. Vishal will be the right person to answer that.
Okay, so yeah, I'll do that after that.
Okay. So for now, if you are able to follow until this part without the KKT conditions and then the Lagrangian function, then that's going to be good enough. Okay.
So in theory also you won't ask KKT conditions.
No, we won't be asking theory also. So since this is revision and then we won't be asking that, we will not be getting into that part. Okay.
Okay. So what type of theory questions can we expect?
Like from week 10, mostly you'll not be getting any theory questions. You'll just be getting the problems. Okay.
Okay.
So like from other weeks, Vishal will be handling. Okay. So yeah, thanks everyone. Okay, it's up to you, Vishal.
Sir,
Thanks, sir.
sir, what about that primal and dual?
Yeah, the primal and dual, it comes under this KKT conditions and the Lagrangian functions, right? So we'll not be concentrating on that. Okay.
Okay.
So, but then is that the method only that you showed earlier? That is to convert two variable function into a single one and then apply the derivative and equate to 0. Is that
That
the
is-
only way?
It's not the only way. You can actually solve it using the Lagrangian, but all I'm saying is you could just directly solve it using the analytical solution part. Okay, without going for the KKT conditions on the Lagrangian one, we can directly solve it. Okay.
Okay, sir. Yeah.
Okay. So thanks, everyone. Okay. It's up to you, Vishal. Thanks.
Yeah, Ram, thanks. Okay. So I'll just, are you able to hear me, right?
Yes,
Yes,
sir.
sir. You are audible, sir.
Okay, I'll just share my screen. So I'll start with the, okay, week 9 was left, right? Okay, I'll start with the week, sorry, 9 or 10, week 9 is this.
9.
So I'll go through the lectures also, but I'll just tell you the important topics that if somebody has not revised much, you can just focus on these topics. Okay, so there's one question related to. Okay.
So what
So-
type of theory questions will come from week 9?
There won't be any theory questions from week 9 to 12.
Okay.
There won't be any theory type of problems. Yeah, there can be problems related to constant function or objective function, but that is not like theory. Like if you have been given some condition, you should be able to write the constant function and the objective function of that condition, whatever you have been given. Okay.
Sure.
Yeah. Okay, so the first important thing is from the 9th week. So 9th week mostly consists of you're able to solve the constant problems. Okay, so the mostly in 9th week. So I'll just go through the brief point, then I'll explain you all the points. So in the 9th week, we are just explaining about the how to solve the objective function. If you have first condition is if the constant function is in some inequality, and the second is if the constant function is in like some equality constant. Okay, like for example, if you have to minimize some function minimum of fx, and then the constant function is like in the form of inequality less than equals to something 1 or so. This is the first type problem that we are solving. And the second type of problem is like we have to minimize some objective function, and in that function we have the constant as equals to some constant. Okay, so this type of problem generally we are solving, and then we'll see the convexity, convex set, and the convex function. Okay, so this is the 3-4 things that we are generally studying in week 9. And in the last, we'll see the how generally we see if a function is a convex or not. For that, we have a very good like method from like if we are able to convert that into a Hessian matrix, then we can say regarding the convexity of the function. Okay, so the most important thing from the week 9 I'll tell you is the Hessian matrix, that if you have been given some function, you should be able to write the Hessian matrix. Okay, that's the most important thing. The second thing is this type of problem can come like, for example, like somebody is asking, you can solve with the basic approach also, but Lagrange can also help you in solving in a like sort of, even both are almost same, but yeah, Lagrange is a pretty simple one if you're able to solve. But the problem, it's not the problem, but if you're solving with the Lagrange, you can get some 2-3 values, and then after putting the values, you need to check whether you are getting a minima or maxima at that point. Okay, so that's the one thing in the Lagrange multiplier. And if you are solving with the basic approach, like for example, I'm giving one example. Like you have a plane, okay, and if you have been asked to calculate the minimum distance, this problem was there, right? In the, I guess somewhere I saw in the graded or practice. So for example, this is some plane r equals to 0. Okay, and then you can, this is the x, y, z. Okay, so okay, so you need some constant, like some constant also. Okay, I'll go through the practice assignment. There may be some problem where this type of problem we may face, right?
So there is one y is equal to x2 plus 1 at one question graded.
Oh, okay, I'll just go through that each and every slide, then maybe I'll go through the same problem. So I'll just telling you this type of problem can come and you can solve with the help of Lagrange multiplier. Okay. And the third most important thing is you should be able to, if you are not able to write a constant function and objective function, then you can't do anything, right? Like you can't solve that problem to get the minima, the value at which the function is minima or maximum, right? So this is the most important thing. You should be able to write the constant function, an objective function, and then if you've been asked to calculate some minima, maximum, whatever it has been asked, you can calculate with the help of Lagrange or with the basic approach also with some smartness and all. And the third is, the most important thing is you can expect some problem from these topics. Okay, Hessian matrix should be able to write. Like for example, if we have been given to write the Hessian matrix for, there was an e to the power z or what. Okay, I'll go through the lectures and then I can't remember the same problem. No, like right. So I'll just go through the slides once. Okay. So this was from the 9th week. Okay, so if somebody has not done much, so at least you should be aware of this all problem. I guess this includes your whole topics, whatever has been discussed in the 9th week. And the last 2 weeks, I'll just go through once simply, and then I'll start briefing all the things. So from the last 2 weeks, there won't be much problem based on probability stuffs. Okay, like not much difficult if you are basic knowledge regarding the basic properties of the probability, basic properties, or you can say you are able to calculate the marginal density function or the joint. You already know the relation between marginal, joint, and conditional. Okay, this all stuffs will be there, and you've been given some sort of to calculate the probability, like basic, not it will not use any of the detailed, like whatever you have done in the stats 2 or stats 1. It will not be much complex problem from the probability. Okay, and that one most important thing is the transformation problem you should be able to do. You should be able to calculate the Jacobian matrix. So this type of problem you may face in the exam. And expectation and variance properties, this is most important thing. If this is an independent, how will you use the linearity property of the variance? If this is a like a correlated, then what's the basic formula of the covariance matrix, even for the correlation also. But yeah.
So it will be there both for continuous and discrete, or mostly for continuous, I mean.
It will be for both. Okay, discrete and continuous both, but there won't be much problem. Okay, so but I can't say directly whether it will be from discrete or continuous, but both mostly have the same properties, right? Wherever there is a discrete, you just have to do the summation. Wherever there is a continuous, you just have to integrate.
Sir, correlation means you have to find some correlation between two random variables, or what?
Yeah, correlation is that one only, right? You have been given, there is basic formula, right, for the correlation also. Covariance matrix you have, with the there is a relation, right, with the standard deviation, covariance, and correlation. So the basic formula regarding that, and these are all like Markov's and Chebyshев. You already did it 2-3 times. And you can, yeah, and this is also important, MLE problems, maximum likelihood problems from the Poisson. So you can, what you can do is you can just remember how generally you estimate the parameter for the Poisson or for the exponential for the norm. Okay, so this 3 distribution you can remember, because there won't be any formula regarding that. Okay, so for the Poisson, for the exponential, for the normal, you can just, like for example, lambda generally we estimate, right, for the Poisson distribution. How generally we estimate? We just first write the likelihood function and then we differentiate it to get the estimated lambda. Or similarly, we can do it for the exponential also. Similarly, for the normal, if one nu is given, you can estimate for sigma square. And if it is been given for sigma square, you can estimate for nu, right? Okay, so these are
Yes,
the
sir.
brief thing that was important for exam, and I'll just start explaining you the concepts, and I'll take some problems from these all topics also. Maybe that will clarify. So if somebody has not seen much of the lectures, you can just go through these all topics. I don't think so there will be any problem in solving any of the problem from the quizzes. Okay, if you are able to solve this one. Yeah, this ML is same as whatever you have done in stats. Okay. So week 9. So from the first lecture, so these are all mostly in the week 9. The proofs are there. Only something like 1 or 2, like 4 or 5 concepts is there. I'll tell you the concepts. These are all many of the time like these are like from the starting. Sir has discussed like if you have some objective function and constant inequality constant has been given, then what are the conditions? What are the conditions that will check? Okay, this x star is the value at which the function is minimum or not. For those cases, like firstly you will check whether it's satisfying your constant function or not. If that is satisfying the constant function, then you can check for whether there is any. So there won't be any addition direction that should be a feasible direction. Addition direction, I guess you already know. So addition direction is like
So,
yeah.
sir, in the week 12, there isn't a problem on based on Gaussian model. So is that important? Like the last question, I think it's from practice or graded. I just don't remember that.
Okay. So just a basic, I'll tell you the Gaussian model you already know, right?
Yeah. So like, that's important. That's a topic. I just wanted to know that's important.
So you should be able, it's not important for the exam because you can't prepare some question on that because this has not been discussed much in that.
Yes, that's right.
And yeah, that's why the question can't be prepared, but you should be able to know the concept because that will help you in the upcoming courses. Okay. The basic knowledge should be having regarding the Gaussian model.
Yeah, only one question is there, so that's why.
Yeah, and that is also pretty simple one. Like,
okay.
So,
thank you, sir.
Yeah. So when I'll come to 12th week, I'll tell you the important topics. Mostly the MLE, Chebyshev, Markovs is the important there. EM model is there, but EM model like EM algorithm is there, but from algorithm we can't prepare some questions. Okay, so that's why EM algorithm you should be able to know what is that, how does it work, but the mathematical question is pretty difficult to prepare from those topics. Okay, so that's why it's important for you to know this is a good way, like it's a good, like you'll be learning more about that different type of model, the techniques, ML techniques and all. So that will help you there because one of the good technique of clustering model. So it will help you in the upcoming courses, but it's not much important for the quizzes at all. Okay.
Oh, thank you, sir.
Yeah. So in the first, we are just solving the constant optimization problem where sir has just proved how will you check whether this X star is whatever the X star you have calculated is minimum. X star is that value at which the function is minimum or not. For that, you need to check 2 conditions. The first one is that it should satisfy your first, like it should satisfy the constant function, and there won't be any decent direction that should be a feasible direction also. Okay, so like if you are able to find any decent direction that is feasible also, then that X star is not your X star is not that point where you will get the minimum value. Decent direction is simply any direction that reduces your function value, right? So if like for example X star is the minimum value, and even after that X star, if you are getting some direction where the function value can be more decreased, okay, so that means this X star is not like the X star is not the required X, because if you are getting some direction where you can even reduce the value of like function, that means that function would be the minimum value. That's why there should not be any decent direction. That is feasible direction is simply if like whatever the value, like for example you are just sliding, okay, like for example this is a direction, okay, this is a function, and if like for example this was the X star in the starting somebody has told me, and even I'm getting this descent direction, right, even after sliding for, and now if we are even after sliding is like we have got this direction, like this is a descent direction I got, and after that getting this descent direction, even at this x, like for example, this is x1, okay, and at this x1, even if like the constant at g star itself, my constant function was satisfying, was less than equals to 0. So at this x star also, if a function is also satisfying me, like satisfying our constant function, okay, that means this is a feasible also. And if this is a decent and plus feasible also, that means x star x1 will become my minima. Like x star is minimum value, like at x star the function is minima, like the value is lesser than whatever we are having at x star. That's why professor has told, like if you are able to get some direction, then that x star is not the correct or the minimum. It's not the correct solution for us. Okay, that is what has been discussed in the first lecture. Okay, so yeah, so this is discussed. Okay, now we'll move to the next part. So even if like for example, it's not as important, but I think so you should be able to let the decent direction, which are the decent direction, like for example, this is f star. If I'm having the del of f star, then what if, because we need to get the dot product as less than 0. So all the function which are like at this whatever the green section is the mostly the decent direction for this del of f star. And similarly for del of g star, because we need to get the feasible direction also. So we can see that there is so much of common direction where where you can get the feasible as well as the decent direction. That's why the x star won't be the correct solution for us, because we should not be having any of this condition, like any of this decent plus feasible direction. Then only if we are not getting any of this, then only you can say this x star is the correct solution for us. Okay, so these are all the theory part. In the second part also, this is almost similar, but here we'll conclude we will get a conclusion. And that conclusion is like, for example, for the constant, for the objective function, where we are having the constant function in the form of inequality, we'll see this for this del of fx, we were able to get this yellow part as the decent direction. And but for the when we are seeing this, that the del of this gx is perpendicular, like it's in the anti-parallel of this del of fx, we saw that this is the feasible direction, that is in the green part, and there is nothing common. Okay, and if there is nothing common, then this x star can become our minima, right? And for that condition, because we already know this is the anti-parallel to each other, so we get a one conclusion, right? So this conclusion is what? Del of fx star is equals to minus lambda or del of gx star, right? So this is the one conclusion that we made. Similarly, we can make for the constant function where we have the equality, like they have gx equals to 0. For those conditions, because for gx equals to 0, we have this straight line that is in the red color, will tell us, or not for this red star, like for example, okay, so g star is here. So this perpendicular line to this g, the direction of the delta of g star, the perpendicular direction to that direction will be showing us del of the direction where this d transpose like dot product of this del of gx star will be 0. So this is the direction that we are getting. So we can see that for the objective function where the constant holds some equality, we can conclude that other conclusion. So that other conclusion is what? So this is the other conclusion. Even this is a anti-parallel, that doesn't matter, because if this is a parallel also, if we're having parallel, so del of fg, for the del of fg, the feasible the decent direction would be the yellow part, but for the del of gx, the feasible direction would be this straight line that is perpendicular. So there is nothing common in that. Okay, so that's why here also x star can be one of our solutions. Similarly, if we'll do for the parallel or anti-parallel, in both the condition you can see for the del of fx, the decent direction is the yellow one, but for the del of gx, the direction is this straight line that is perpendicular to that of del of gx star. Okay, that is how we got this. So this is how we concluded this. Okay, this can work, and this is generally termed as Lagrange multiplier. So whenever you will get some objective function plus some constant equation, so what you will do is you can try to solve with this. Even the one that Ram told, okay, that is fine. But with this equation, if you have some constant will given, okay, in that problem, the constant, I guess, was not given. But if you have some constant and the objective function, you can solve with this.
Sir, constraint was also there in that
Okay,
problem.
what was the constant there?
Something x cube plus y cube was there.
Okay. For that problem you are saying, I thought of x square. Okay, so yeah, so I'll take some problems. Okay, maybe in the like lectures also sir has taken, but I'll take from the practice diagram graded experiment also. There are some problems. Okay, that is been solved with the help of constant problem. See, all the problems. See, that was a pretty simple one. That is how with the basic approach also. See, all the problem can be solved with both the approach. That is fine. But if you have been given the equation in the form of the constant, that is in the form of inequality constant, difficult to solve with the basic approach. It will be solvable, but you need to get some smart solution. Like, see, for example, I was telling you to get the point that is perpendicular, the minimum distance from that.
Sir, I think there is yeah, there's a
Okay,
disturbance.
so from this from yes, it's coming from Ashwin. Just mute it. Okay, is that fine? Fine, right? So okay, so as what I was saying, so if you have to, like I was telling you to, like, if you have some problem, some objective function that like you would have solved in class 12th, so you can solve with a basic approach also, but Lagrange will help you to solve in a better, like in a quicker way. Many of the problem can be solved, not all the problem, but most of the problem that will be asked in the exams and all will be able to solve with the help of Lagrange multiplier. Okay. Is this clear?
Yes, sir.
Yes, sir. Sir, can we see some examples, sir?
Yeah, I'll just go through that some problems I'm having. Yeah. So this is the graded
Sir,
or
so
practice.
if the constraint is less than equal to, then we will use minus lambda. And if it is a equality constraint, then we will use lambda, right?
So even if you are using lambda each time, so the lambda condition will get adjust itself. Like if you are putting minus lambda, and if you are getting lambda as 2, and if you are putting lambda only, so at that time you'll get lambda as -2. Okay, so it will get adjust. So don't worry about that. Is this clear?
Sign doesn't matter.
Most of the if you'll solve, whenever I used to solve, I just take the lambda and I get the value. So I guess the sign, because the lambda will get adjusted. See, whenever I'm taking minus lambda, I'm saying lambda should be a positive value. Okay, if I'm just taking lambda, then at that time lambda can be negative also. Is this clear? Are you getting my point?
Yeah, but the answer then, I mean, lambda should be positive for a
Okay, I'll tell you. So this is the problem, the distance of the plane from the origin. Okay, so this is yeah. So what is the objective function for this problem? The objective function would be what? We have to get the distance from the origin, okay, from 0, 0, 0. So the objective function for us would be from 0, 0, 0. What would be the distance if I'm taking just x, y, z as some point? So distance would be what? X square plus y square plus z square, right?
Yes, sir. X square plus
Okay.
y square plus
And that point should be from this plane. So our constant function is this one, and this holds the equality problem for us. So I can just write as del of f equals to lambda. I just took lambda, right?
But sir, this is equality constraint, no?
Okay,
X
yeah.
plus,
So, yeah, you are correct. Yeah. Okay, so
Sir,
even
if the point is not origin, how we should solve, sir?
If that point is not origin, so give me a
so
condition.
we will subtract
Yeah,
the points, right? X minus a whole square.
Yeah,
plus
x minus a ka whole square plus y minus b ka whole square.
It is simple distance formula, right, sir?
Yeah, it's a simple distance formula.
Yes.
And sir, if we have to solve by analytical method as suggested by Ram sir, so we will not neglect the root, right? We will take the function as root of x square
Those
plus.
problems, see, if you are approaching, like for example, this is the plane, and you need to get, so See, basic approach, I guess for some problem you can directly say for this plane, this is a plane. You can solve here also. So, but you should be aware of so many other concepts. Like for example, this plane I know. So I know the basic concept of the plane. Okay, plane generally, if this is the equation x upon a plus y upon b plus z upon c is the equation of the plane, ABC generally represents the direction cosine or the direction ratio of the perpendicular direction. Okay, so I have the direction ratio of the perpendicular direction. Okay, and if I'm putting some, because I need to get the minimum distance from this plane. So this plane I can just put it some value x, y, z, and this is the distance. Okay, so what I can do is, okay, so for this equation I can do one thing. I can get the slope of this line, right? Okay, yeah. One thing I can do, I can get the direction ratio of this line. Direction ratio is simply this point upon x2 minus x1 or y2 minus x. So I can get the direction ratio of this, and I have the direction ratio of this. Then the product will be 0. From there we can solve. But that's the issue. If you are solving with the basic approach, you should be aware of so many other conditions also. One thing, right? Like for example, many of you are not aware of that what is direction quotient and what direction ratio for the plane equations and all. So that's why it's better to go with the Lagrange multiplier in this condition. Okay, but if you have been asked to solve what is the distance from this against circle, and also I guess many of you are aware of that equation. So in those problems, I guess you can solve with the basic approach also. But if you are not aware, you can just go with the Lagrange. What's the problem in that? You have the objective function, right? You have the constant function. Okay, so you can solve with that equation fg equals to minus lambda g of del of g.
Yes,
So
sir.
whenever there
Better
is
to
a
use
yeah,
Lagrangian only.
That's
yeah,
a
go with
easy
the
one.
Lagrange. And if you are seeing this problem as pretty simple one, you can solve with the basic approach, then you can solve with the basic approach also. There's no problem with that.
Why you taking minus, sir? Because we used to take only, because plus minus get adjusted, na?
Yeah, plus minus will get adjusted. Okay, you can write plus also. For equality, since the professor, whatever the professor use, you can use the same thing. For the inequality, you can use minus, and for the equality, you can use just plus. It will get adjusted in the end, but you can solve with both the approach. You'll get the same answer.
So one question, sir, in the while we are solving this through Lagrangian method, suppose the constant function is given. Say, I am just saying one constant function, 2x plus 2y is equal to 20.
Okay.
Sir, I just reduce that to x plus y is equal to 10, and I am landing in a wrong answer.
Yes, sir. The lambda value is different.
Okay. See, so lambda value is different.
There is a practice assignment problem number 10. You can refer that.
Okay, problem number 10, right? This is the problem. This is the equation, right? This one.
So this is week 10.
Week 10, you're saying. Week 10. Okay, week 10.
Week 10 or week 9, I can't remember that one.
Week 9, so I don't think so there is any problem.
Sir, in week 10.
Okay, week 10. This is a problem?
No, not this one.
No, sir, it's in week 9. If we simplify, our lambda is being half.
Yes.
Is it Sumit?
Yeah.
weak R4. Yes. Practice, you told, right? Practice. This one?
Yes.
Okay. So into the value of okay, so this is what you're saying. So lambda should, okay, if you are taking minus lambda, then it will become minus 2.5, right?
No, not minus lambda, sir. If I simplify that constant equation, 2x plus 2y is equal to 22, x plus y is equal to 10, then
At that time the lambda will change. But that should not, okay. I'm getting your point, but this is the, I guess, the problem can't be asked like what is the value of Lagrange multiplier, because if you will multiply, see, then you should go with the same problem to, because if you are differentiating, you'll get 2, right? So the lambda, I guess, will change. Wait.
Sir,
Okay,
even if it is 2 x plus y equals to 10, then also you will get same, right?
Yeah, so one, wait, I'll just calculate this. If you'll calculate, so del f of del x is what? Y, right? Y equals to, so okay, tell me the equation. What is the equation here?
2x plus 2y is equal to 20.
So if I'll write it here, equals to lambda times. So if what is the function fx is this one, right? This is what has been given. And 2x plus 2y equals to 20. So this will comes to y, and this is x, right?
Yeah.
And here you will be having 2, and here also 2. So y equals to 2 lambda and x equals to 2 lambda. Now what you have to do? Now what you have to do is you have to maximize upon the, I didn't saw this. So this is the start.
Maximize xy area.
Okay, so lambda you are getting y upon 2 and x upon 2. That's fine. So there will lead to x equals to 20. Okay. So if you are getting same thing here, so y and x is equal.
So can't we put x and hello? So since x is equal to y, so we can put this into the constraint and get 4x is equal to 10. 10.
Yeah, this is equal to, okay, 4x or 4y.
4x, so whatever it was, I'm not sure whether it was 4. 2x plus 2y, so it will become 4x is equal to 20. Yes, sir. So x will come to 5 and y will also be 5. So from there we can find out the Lagrange.
Yeah, so this is lambda. So okay, so if I'm doing with the x plus, so from here I got 2.5, and if I'm doing with x plus y equals to 10, right? Then I'll get it here. I'll get 1 here. So there also we'll get x equals to y equals to lambda. If I'll solve it here, x plus y equals to 10. So I'll get what? I'll get 2x equals to 5. Okay, from here I'll get, sorry, 2x
Still you
equals
will
to
get
10.
lambda as 2.5, right? No, you will get 5.
No, 5 we are getting, right? So that is what I
Yeah.
was telling. This, if you will change the equation, so even the equation is same, you'll get, so the problem with this is you can't ask the value of Lagrange multiplier, because that lambda, that is what I was saying, it generally get adjusted. If you will change it to 3x plus 3y, the value will change even if this is the same equation, the ratio. So if somebody is asking you to calculate the Lagrange multiplier, so you can solve the equation, like you can solve the max, like whatever the objective function has been given, either to maximize or minimize. In those conditions, you will not face problem because the lambda will get adjusted, and if you will put the value, it will behave in the similar fashion. But if you are just asking the value of lambda, it will change whenever we'll change the equation, because it's generally the differentiation part we are doing. If we are changing the coefficient, you'll get the different coefficient in the differentiation, right?
Sir, so better to use the equation as it is given, not to reduce.
So,
it,
but
right?
I don't think so anybody will ask you to calculate the Lagrange multiplier. Okay, this was a practice assignment, so this is fine. But in the quizzes and all, nobody will ask you to enter the Lagrange multiplier value. Even if they are asking, don't change the. But both the equations are same. Then why it is changing? I don't know. Even
Sir, maybe is it because if we divide by 2, that grade g xy, then we have to divide grade f of xy divided by 2 too. Because they are in proportional.
What x equals to y equals to lambda we got here. So what are you saying?
Yeah, we are like when we are simplifying grade g, at that time we are dividing that grade g by 2, right? So
Yeah.
I guess we have to divide grade f by 2. Then maybe lambda is same.
I didn't in the first. I didn't get your point. Can you repeat that?
Okay. So what I'm saying is.
Your voice is not audible.
Divide the equation by 2, we'll get x plus y equals to 10, right?
Yeah.
Yeah, so I guess we have to divide grade f also with the 2. Sir, I'm trying. It's okay. You go ahead. I'll try and let you know.
Okay, it's fine.
Because I'm not sure.
Yeah. So I'll just start. Okay, it's fine. But okay, it's
From
fine.
KKT, can I ask it now?
Yeah.
KKT.
Okay. KKT condition will be discussed by Ram only, I guess. Ram didn't discuss because I guess he was having some session.
So the issue is very minor. Just I don't want you to solve
Yeah.
anything. Just
Yeah.
minor. Sir, in practice assignment questions and in the graded also, the constraint was greater than equal to 0. In the mock also, in the mock paper also, we have the same constraint, greater than equal to 0. But in the mock solution, we have to change the inequality signs, make it to the standard form less than equal to 0. But in practice and graded, we did not do that. So is there a particular reason for that?
I'm not pretty sure because some weeks are handled by some persons. So whoever has created that solution, so I guess Ram has created or.
Sir, but using that solution which is given in practice and graded, we are not arriving to the same answer. That is the problem. Like if I don't change it to the standard form, or at all if I change all the 3 practice, graded and mock into the standard form that is less than equal to 0, I should arrive at the same answer.
Yeah, correct. Mock solution for the last one, right?
Yes, sir. Yes, sir.
And sir, many answers in the mock question is wrong, sir, actually.
Can you tell me which one?
So
Sir, one is with that error question.
yes, the error question is wrong, sir.
Yeah, this one.
This is, I mean,
This
data
one?
is something and here the calculation table is something. Although written the equation is something and calculating value is
This
another
one?
thing.
Which
Yes,
problem?
sir. This one, sir. Here the problem is said ki the intercept and the slope is 1, and 0.5, 0.25. But the equation is making it something else. Even if I take the equation.
Okay. So what happens now? Many a times, what happens for like this would be a problem that has been asked already in the quiz. So earlier, what happened? What was happening? We were preparing 2-3 sets. Okay, so some sets we were just, I guess that's the printing mistake, or maybe the person who was preparing the question, he had just mixed up. Like in set A, he would have asked this one, and he has just put the solution from the set B. I guess that's the problem, I guess.
And also when I check the answer in the portal, it is also showing wrong. Although answer is.
Okay, so this problem you are saying this problem, right? Second one.
And then again you go down, sir.
Yeah.
Go down little.
But sir, anyways, KKT conditions
This one.
aren't that important for this final exam, right?
So yeah, KKT condition won't be asked because the problem from the 10th week has been created by Ram itself. So if he's saying, so there won't be any problem.
Sir, go down, sir.
Okay.
Yeah, hold on. So this problem, my answer is 5.48 and 4.64. But in the portal, it is showing it is 5.4859. I don't know.
So don't worry about that. I'm like for the mock, and also we didn't give. So in the starting, we thought of giving the range also, but like maybe in the hurry, we have just released it with the exact answer. Okay, that's the problem. We generally give the range, like a big range. Like for the last quiz also, for some question I gave range like 5 to 6, some sort of things like that. So don't worry about that. So if you are even like 4, like in the exam, the range would be like 4.5 to 5, something like that. So don't worry about that. Okay. So this is the mistake that. Yeah.
So can go to the previous question.
Which question?
So the previous question, the mean squared question.
Question number?
The KKT one, sir.
No. So mean squared error question. I think it's question number 2.
2.
Okay. This one? Find the equation of the tangent.
No, sir. Downwards. No. Question 2 below that.
3 questions. Yeah.
Yeah, I guess for this question also there is some error, right? There is some
So
error.
no, sir, not this one. So mean squared error, the question, the very first question which we have just opened in this mock.
Very first problem. This is a
Sir,
supervised.
Request.
Yes, sir, below this.
Yeah, this one.
It's below this question.
Excuse me, sir.
Yeah.
Can you do the revision kindly so that the doubts be at the end? We are all waiting for the revision session, and if you can solve that, it will be very helpful. These things we can post in the discourse and get it clear, please.
Okay, so I'll take this doubts in the end. Okay, so maybe we can just this.
So
just
the KKT one. So just one thing here.
Yeah.
So here, if we are putting the values like x and y, then we're not getting in the equation also. We are not getting the same like 3, 5 answer. I'm getting here 1.5, and all those the way downwards for YA the values are different for me.
It's different from here, or you are getting the different value in the solution. So that is what I was saying. Maybe.
So what I am getting is very different.
Okay, so maybe we can discuss in the end. Is that fine? I'll just solve it, then we'll see whether the answer is given is correct or not. So, okay, in the end, I'll just go through the mock ones. Okay. So I'll just go through the concept in a like 30 to 40 minutes, and then we'll go and solve some problems.
And so also some practice assignment questions from week 11, which I was
Yeah,
asking
I'll
in
do
the
that.
beginning.
First, I'll just go through the week 9 and 10, like 11, 12, 7. So, okay. So
Okay,
where we, okay. So yeah, so till now it's clear, right? So this is a like Lagrange multiplier that we have concluded. Okay, so we have concluded two sort of things. If if we are having the objective function needs to be minimized, and if we have some constant function and that constant function is in some inequality form, then we can write the equation like this. Okay. And if this is in the form of equality, the first one is inequality. Inequality means both should be anti-parallel. Okay. And for the equality, it can be anti-parallel also, it can be parallel also. So that is how, so this here the lambda can take any value. That is why I was saying it can adjust itself. Okay. So this is the Lagrange multiplier for you. So yeah, so there are some problems that has been discussed in the lectures also. I'll just go through the same problems. Okay, so this was the objective function that you have been given here, and this is the constant function. This is the constant function that equates to 0, and this is the function that you need to minimize. Okay, so what you will do is the base pretty simple one. You just have to differentiate it with respect to x, like whatever the function, like variable you have been given. Like for example, here x1 and x2 has been given. You have to differentiate it and equate it to the del of gx. So the simple one, and then you will get the value of lambda. So here we got the value of lambda from here. Lambda can be, what is the lambda here? -1. Okay, and it can be, I guess, what is the value? Yeah, so lambda is -1 for here. And if we are getting the lambda as -1, so we can put it in here to get the value of x and y, x1, x2. You can get more than one x1 and x2 for any of the problems. So what you will do, maybe you are getting one x1 for the maximum and one for the minima, or maybe for the other values also. So what in Lagrange you have to do, after getting the value of x1 and x2, whatever the values you are getting, maybe 2, maybe 3, if you are getting 2, 3 numbers, just put that x1, x2 in the equation and get the minima. If you have to calculate the minima, just see for which x1, x2 you are getting the minima value. Okay. So if you are getting x1, like for example, for x1 dash and x2 dash, you are getting the minima, that x1, x star is the minima for you. At that point, the equation is getting minimized. Okay. I think this is pretty clear, right? So for example, here we are getting x1 as this both, and also we are getting, I guess, yeah. So this also we are getting, this also we are getting. So this is the minimizer and this is the maximizer that you need to put and check whether for which x star you are getting minima and for which value you are getting maximum. Okay. And the projected gradient descent is not important for the exam, but I'm just telling you for the conceptual purpose, it's not important at all for the exam. Okay. So what we used to do in the earlier, we used to solve many of the problems with the help of gradient descent. Okay. So projected gradient descent helps us when we are having something like, for example, whenever, like, why do we start reading the Lagrange multiplier and all? So many a times what happens, Lagrange multiplier also will just have, yeah. This also getting. So this is the minimizer, and this is telling you for the concept whether for which x star you are getting minima and for which value you are getting maximum. Okay. And the projected gradient descent is not important for the exam, but I'm just telling you for the. What is this repeating here? The voice is repeating what?
Yeah, your voice is got confused.
Okay. I don't know how does it work. So okay, I'll just start with this again. The projected gradient descent. Okay. So many times what happens, we are not able to solve the problems. Okay. So the gradient descent was good when we were having when there was no any conditions, then we used to use the gradient descent. Why we were using? Because there was no boundary on the constant function. So if there is no boundary on the constant, we can use the gradient descent nicely. But if there is a boundary on that function, like for example, we have the constant equations now. So if we are having the constant equations, so in those conditions, because if you are having the constant equations, like for example here gx is less than equal, gs must be less than equals to 0. So we are putting some conditions here. So if we are putting some conditions in the gradient descent, x can go anywhere, right? So that is why we have started doing projected gradient descent. And the projected gradient descent, like for example, in the gradient descent, what we were doing, we were just subtracting with some step, we were using some step count, and with some basic formulas, we were taking the step count and then reducing the value from the reducing the point and then seeing. So we need, what we were doing the gradient descent, we were just updating the value of x with the decrement of the x. Okay, we were decreasing in the some descent direction, where we descent direction means where we are able to see some x where the value is decreasing. Okay, so we were just updating each and every step, we were updating with some eta, and eta at there we were eta was representing the step size or step count, whatever you want to say. Okay, but if so, from here xt plus 1 can go anywhere. Okay, that so xt plus 1 can go anywhere, that can go out of the constant function also. So to bound it, we started using the projected gradient descent formula, or projected gradient descent concept, where what we started, we just use the concept of projected operator. Okay, so that what it was doing, so it was just, if I'm getting out of the constant function, so what it was doing, it was just minimizing those values. So whichever the value that is very much closer to that constant function, we were getting to that point. Okay, and from that point it was helping us to calculate the minima value. Okay, so it's a pretty, like, I'll just tell you in one line. So earlier we were not having any condition on the constant. Now I'm having condition on the constant. So I started using projected gradient descent. And in the projected gradient descent, we just started doing one projection operator to projected projection operator. Okay. Yeah. So now it's clear, right? The voice is clear, right? Maybe.
Yes, sir.
Yeah. So now we have started using the projected gradient descent because of the constant problems. Okay. So but this is not important for exam. There is not much problem that can be asked from these topics. Okay. So now, is it clear to everyone? I'll move to the next part.
Yes, sir.
Now we are starting with the convexity. Okay, so the convex set. The convex set generally, like for example, S that generally belongs to some real of a d-dimensional is a convex set. If for example, if any of x1, x2 you are taking, x1, x2 you are taking from that set, and then if you are doing this some computational, if you are doing lambda x1 plus 1 minus lambda x2. Okay, if you are just taking any of the x1, x2 and computing this one, and if this is coming in the S set, okay, then this is a convex set. So, and there the lambda should belongs to, from the lambda should be between 0 to 1. So I'll tell you once again, if you are having some set S that is the convex already, okay, and that belongs to some RD. If this S is a convex set, if you are taking any of the x1, x2 from that set, okay, and then doing this computation, that is lambda x1 plus 1 minus lambda of x2, where the lambda should be between from 0 to 1. So lambda can't exceed 1 and lambda can't be less than 0. And if that computated number is coming in the same set S, then it's a convex set. Is it clear?
Yes, sir.
Yeah. Okay. So this is the convex set so yeah, so this is the convex set mostly. And so there are many methods that are there in the, like, if you will just go through the slide, you can get to know what are, like, if you are taking the intersection of two convex set, you'll get the convex set. So yeah, so this is there for the convex sets. The most important thing is to know regarding the convex function. Okay, so the convex set equations from the figure also, or there are many methods that has been discussed, like from the epigraph also you can say regarding the convex function, convex sets and all, right? Now there are like 4 or 5 properties. If you'll just go through the slide also, you'll be able to understand. The first thing is the intersection of the convex set is always convex. Or for example, the second one is the same thing we are writing in the form of like x1 till like S is a set where x1 to xn is belonging to that convex set Rd. And if you are taking if you are taking some lambda 1 to lambda, it's a pretty like the same one in the expanded form. So that we have discussed in the starting. If you are taking any of the x1, x2, and then doing some computation on that, there also the summation of lambda was 1. Here also the summation of lambda is 1. But the z here is after computing the z, you'll get to know a concept that is the convex hull. If any point inside the convex hull, all the points inside the convex hull will be a convex, like will come under that same convex set itself. Okay, so this is the concept, the second properties of the convex set. And then there's the then you'll start getting so from here it is important for the exam also, the convex function. So yeah, so from here it is important, from the convex function it is important now. And for the convex function, the most important is if you have been given in the form of functions, you should be able to write the Hessian matrix. Okay, so this is the most important thing. You should expect some questions from there, from the convex function. That means you should be given some equations or some equations, and you need to convert that into a Hessian matrix. Okay, and if you have been asked to anything regarding the that matrix, you should be able to say whether it's a positive definite or positive semi-definite or whatever you've been asked to say. Okay, if that is a positive definite or positive semi-definite, you can say it's a convex function. Okay, is this clear to everyone? How will you be able to, like, if you have been given some function, you'll be able to write the Hessian matrix? Yes, everybody knows that how to write the Hessian matrix, right?
Yes, sir. Yes, sir.
Okay. Anybody is having any doubt in writing the Hessian matrix, you can ask, because it's important for the exam. That's why I'm just repeating 2-3 times.
So can we quickly take one example Hessian matrix, sir?
Okay. So Hessian matrix, simply whatever the equation you have been given, okay, any equation if you have been given, right? Like for example, sine of some xy, okay. Okay. So if you have been asked to calculate the Hessian matrix, so Hessian matrix is what? So whatever the function you have been given here, so just write it del of del x, del of del y, del of del z. Similarly, you can do del of del x, del of del y, and del of del z. So the intersection is what? You have to differentiate this function twice with respect to x. Okay. What? Can you repeat that?
Here the function is sine of xy, so would it be 2 × 2 matrix?
Yeah, here it should be 2 + 2 matrix. Yeah, correct. So if this is e to the power z, then it must be like 3, right?
Yes, sir.
Okay, x, y, z. So if this is in the form of e to the power z sine of xy, then it will be a 3 × 3 matrix. And what you have to do is, so whenever you are calculating the Hessian matrix, you should, how you can check whether you are getting it correct or not, it should be a symmetric matrix. Why? It should be a symmetric. Why?
Because we are doing the x or y or x is same.
Yeah, so here you are differentiating with respect to x twice. Again, here you are differentiating with respect to x and y both. Again, you are differentiating here also with respect to x and y. So you'll get the same value here. Okay, so that's why you'll get a symmetric matrix. Okay, so I think so it's clear. You have to differentiate this here twice with respect to x, here first with y, or whatever you want to do, first with x or first with y, and then with x or y. Similarly, here with respect to z and x, similarly you can do for all the equation. If you have been asked to calculate the Hessian matrix, so if you have been given something x, y, z, and if you have been asked to calculate the Hessian matrix, at 0, 0, pi, then you should be able to write the matrix, because you will get the matrix in the form of XYZ, and then you can put the value of 0 XYZ, you will get the correct Hessian matrix. Right? Is this clear?
Yes, sir.
Yeah.
Yes.
And after that, if you have been asked to know, if you have been asked to calculate whether it's a convex function or not, and then what you can do, if you calculate the lambda, and if lambda is equals to either it's a 0 or greater than 0, it's a non-negative, then you can say it's a convex function. Okay, so PSD or PD. Fine.
Sir, what kind of questions can we expect from this, sir?
So this is what I'm telling. You will get some sort of problem like this. Like for example, e to the power z sine of xy. You'll be asked to calculate the Hessian matrix at. I'll just mute Yeah. So what you can, so you'll be given some equation like e to the power z sine of xy, and you have been asked to calculate the Hessian matrix at some point like 0, pi, 0. Okay, calculate the Hessian matrix, and then the other question can be whether this matrix behaves as a convex function or not. So this type of problem you can expect. Is this fine?
Yes, sir. The lambda is the derivative, right?
What? Lambda?
Lambda greater than or equal to 0, that is the derivative of the Hessian matrix, right?
No, I think it's eigenvalue.
Lambda is eigenvalue. Eigenvalue.
Oh, sorry.
Yeah. So okay,
Sir,
this is
we
the
can also
eigenvalue.
confirm with
Can you
determinant.
solve this sine xy1 and
The
show us?
determinant of the Hessian matrix is positive and the first element is also positive. Then it is convex, right?
If the determinant, this one is positive.
Yeah, and the determinant is also positive.
Okay, if this is a 2 cross 2, then it's fine.
Yeah.
Yeah, then it's fine. If we are getting this as a positive, A as positive, and the determinant also as positive, then it's a what you can say, the point definite. Yeah, correct. Yeah, so e to the power z you are saying.
In mock,
What?
sorry, in mock, they are said since it is symmetric matrix and all eigenvalues are positive, hence it will be positive or semi-definite matrix.
Semi-definite. If all the lambda I is greater than or equals to 0, this was the condition. This was the condition. Okay, so yeah, so if this is the condition, it's a positive PSD, right? And there's a convex also.
Yes.
Okay, so this is clear, I guess. So nothing much will be from here. So from here you can expect some problems, like I told you, the Hessian matrix, or to how to write the constant equation of objective function, and problems like I told you to calculate the minimum distance, maximum distance, that you can solve with the help of Lagrange. You can take this equation minus lambda del of gx, or you are taking lambda also, it's fine. You'll be able to solve that problem. Whatever the function x value you are getting, just put in the function, objective function. See whether for which of the following x you are getting minima or maxima. If you have been asked to calculate the minima, just put that x star. If you have been asked to calculate the maxima, then put that x for which the value you are getting the maxima out of this 3 or 4, whatever you are getting. Right? Clear?
Okay, sir.
Yeah.
So, I didn't understand this, but for Hessian, both positive definite and positive semi-definite, then it is convex, or only positive definite, the eigenvalues, about the eigenvalues.
No, lambda should be equals to 0. Okay, whether you are getting all the lambda greater than 0 also, it's fine. Or you are getting some 0 also and some positive, then also it's fine.
Okay, oh, thank you.
So in that question, there is no condition given. Mock for n term, question number 8.
No condition. Where is that? Okay, so this question, this one.
On page number 3. Not this one. Sorry, not that one.
This one?
No.
This is only you were asking, right?
In question, it is question number 8. Like this is solution. So
Yes, sir. This
in
one.
here,
This one
numbers
only.
are not same. Yeah,
It is this one, sir.
So this is a positive definite, man. This is positive definite. This is not positive semi-definite.
Yeah, but
And also, there are so many mistakes. So I didn't prepare the mock, so yeah. So this is positive definite. This is pretty written.
But sir,
yeah.
hello, sir.
Yeah.
Sir, in positive semi-definite, lambda is greater than or equal to 0.
Yeah.
That holds true.
no, but one of the lambda should be 0 for semi-definite.
So in semi-definite, there should be some lambda should be equal to 0.
Okay, sir.
If you are getting some
But
combination
sir,
of
in
0 and
positive
positive.
semi-definite.
What?
But sir, in positive semi-definite, we have lambda either greater than 0 or equals to 0. And in positive definite, we have lambda strictly greater than 0. So if something is positive definite, then it must be positive. Sorry, if something is positive semi-definite, then it must be positive definite also.
Yes, that is what.
But
that is what I
this
was-
is not positive semi-definite, right? It has lambda values which are greater than 0.
Yeah, but in semi-definite, we have two things. Now, it should be either greater than 0 or equals to 0. So it's either greater than 0's condition is satisfied here. So
See what happens in
we
positive
can say
semi-definite.
there's a positive semi.
Positive semi-definite generally represents a different type of function. Okay. So positive semi-definite, you can imagine the graph, right? It's a graph that generally has a lot of values where the function is 0, right? So you can get a plain sort of things where the values will be 0.
Sir, if we see one is subset of other. So sir, both should be true.
Yeah, if the determinant of that matrix is 0 and A is greater than 0, the first entry, then it is positive semi-definite.
I need to check up on this. I can't confirmly say, but if, lambda, so whatever you were saying is also fine. Like if lambda, if all the lambdas are only positive greater than 0, so this is a positive definite, but it can come under positive semi-definite also, because the same for the semi-definite we have the condition lambda is equals to 0, where if none of the lambda is equals to 0 also, all the lambdas are greater than 0. So it should be a subset of this one. Right?
If this question is MSQ, then take on both of this, like positive semi-definite, positive definite. But if it's MCQ type, we can go for positive.
Yeah, I guess you are correct. I guess, but I need to check upon that. I can't confirmly say.
Sir,
Maybe I'll check and
week 6 there was condition for positive semi-definite where the determinant of that matrix was 0, and the first entry, that is A11, was greater than 0. So I think we can just think of that. And
determinant is a different thing. Different thing means.
Yes, sir. But sir, if determinant is a product of the lambda values, right? So if that is 0, then it is positive semi-definite.
Yeah.
It is
You are correct.
written
You are correct. You are correct. So yeah,
Because this comes from the week 7, so it should be pretty clear.
so yeah, so if see the one condition is if the determinant is 0, then you can directly say, because some of the determinant of that matrix that you have got, the diagonal matrix, if the determinant is 0, that means some of the lambda values must be equals to 0, right? And if the other one, I need to check upon this, but regarding this key, whether if this condition is satisfying, whether it will be a positive definite also or not, that I need to check. This is what you are asking, right? Like everyone.
Yes, sir.
Yes, sir.
Because when I checked out some material or over there also, it just says that for positive semi-definite, the condition is the eigenvalue should be like greater than or equal to 0. So it does not say that there should be a specific, I mean, if there is 0, then it is specifically positive semi-definite.
Okay.
But within the class of positive semi-definite matrices, we can, if none of them are equal to 0, then we can say that they are strictly positive definite. Like it's like a subset, like within a class of, like we basically take them as positive and negative, right? Like positive, we have positive semi-definite, and like within that class, if you don't have a plane on which, but if we can like take that 0, that minimum value to a particular point, then that becomes like a positive definite class. Because the only, like when I referred a few materials, the only condition they said was regarding the lambda was that the lambda should be greater than or equal to 0 when it comes with semi-definite, and for definite it just says that the lambda should be greater than 0.
Okay, yeah, then okay, then the answer, the given answer is correct. Like then if you are having the MSQ, then it will come under that also. PS, if you are getting some lambda, so this is not the strictly
Sir, so
like,
can we say that PSD is a superset and PD is a part of it?
yeah, you can say that.
Yeah, it is somewhat like that, yeah.
So say if the matrix is positive definite, and if it's a MSQ question, so we should select both of the options.
No. If it's a positive definite, then you can't say it's a,
Sorry,
that doesn't
positive
implicate.
semi-definite.
Yeah, if this is a positive semi-definite, then you can say that.
Okay.
Okay.
Excuse me, sir.
Yeah.
Sir, I want you to please discuss about practice 11 questions.
Okay, so
I'm
yeah,
waiting
so we
since
came to
1
we
hour.
came to that 11th week. Okay, fine. So I guess this is clear, right? So from 9th week, I already told you to practice some questions from the Hessian and practice some problems from the graded and practice itself, and that will be more than sufficient, I guess. From 11th week, I'll start. So 11th week, I'll just take the questions itself. So 11th week, you've already read 2-3 times. Okay. So just tell me the question that you are having the doubts in 11th week. The important topic.
Question number 17.
Okay. So maybe you can wait for 2-3 minutes just. I'll just tell you the important topics I told you in the starting itself. Okay. The important topics from the 11th weeks are the basic properties of the probability. If you have been asked to calculate the basic properties when given, how do every time there are some basic properties like the probability value should be always between 0 to 1. Some density function can go beyond 1 also. The density function should always be greater than 0. So these are the basic properties. The integration should be equals to 1. The area should come under the area under the PDF should be equals to 1. The CDF will at infinity will be 1, and at minus infinity will be 0. Okay, so these are the basic properties you should be able to know. The what do you say, the how will you relate from the marginal, joint, and conditional? So that you should be aware of that. The transformation thing you should be aware. Expectation and variance properties. Whenever you will be given two random variable, whether it's independent or not, Chebyshев inequality, Markov's inequality, and that is more than sufficient for the 11th week. Okay. So if you're having doubt, you can ask. So yeah, tell me the question number. Practice assignment. Which one?
Jacobian part.
Okay, Jacobian part. Which one? Your voice is not clear. Maybe is this problem with me or everyone? Like, her voice is not.
No, sir. It's I think it's a network.
Okay.
Transformation and the Jacobian parts.
Okay. So Jacobian part.
No, sir, not transformation. So not transformation.
Which one then? You can type it on the chat box.
That's question number 70. Without using the solution part, can you go to the straightforward questions because the question number differs in the solution.
Okay, I'll just open question number 17, I guess you said.
Yes, sir.
Graded or practice? Practice, right?
Practice.
7 is suppose the number. Oh, it's a probability with alpha like what is the quickest way to solve this? There's nothing quickest way, I guess, to solve this problem with the number. This is a like
geometric.
You can. Yeah, it's a GP.
Question
we
is,
can solve.
yes, sir. But sir, I'm not getting the answer here, and we are not provided with the solutions also.
Hey, solution isn't provided, I guess. Solution is there, man.
Yeah, solution is,
But
I think, 2 to 3 days
not
before
the
it's
current
uploaded.
explanation. Explanation is not proper there.
See, it's a geometrical distribution. Like, see, geometric distribution, how generally you solve for, like, for example, if you're solving for like for example, probability such that x is equals to some value k. For that, the x equals to k. What's the? It's a geometric.
Can I
Your voice, you can type it. Your voice is not clear.
In this question, this fewer than 6 means I should take the 6 balls, right?
Yeah, you should calculate for 1, 2, 3, 4, 5.
See, x less than k or 5 is there, right? You can calculate by 1 minus probability of x greater than equals to 5, right? What's the?
Excuse me.
I can't hear you. Anything I can't hear.
Sir, can we expect that find the value of k kind of problem from random variables?
Yeah, you can, like, in the geometric, you know, the probability of x equals to some value k is what, I guess this is, I'm not sure, this is 1 minus p to the power k minus 1 and p, right?
Yes.
Okay, and if you are doing the summation for the geometric mean, if you'll do the summation for probability such that x greater than k, just do the summation of this from n equals to x equals to k plus 1 to infinity, 1 minus p to the power k minus 1 into p, okay? And just add it and separate it from the 1, you'll get the answer. From here, the k will be 5, right? This is a solution for this.
Is this binomial, sir?
It's not binomial.
Excuse me,
It
sir.
is geometric.
It's geometric. Yeah.
Sir, am I audible now?
Yeah. Like, not much, but yeah, I can hear you now, at least.
Yes, sir. So what I have done here is I have done the same thing which you have just mentioned here. 1 minus p x greater than equals to 5. And p here, what I'm getting is 1 by 6. Is it right?
1 by 6 to the power. Okay, I need to calculate then. What's this given in the solution?
Sir, here is a doubt. So question is saying fewer than 6 deliveries, right?
Fewer than
That
5 or
means
fewer than 6?
Fewer than 6, sir. So we have to calculate from 1 to 6,
Yeah,
1 to
so
5.
Yeah, then you have to calculate for 6. I thought it's a fewer than 5.
yes,
Fewer than
yes.
6, then k is equals to 6 here.
Yes. That's why.
Sir, if they say it is strictly fewer than, then I should take up to 5, right?
Strictly, it's not like, it will not mention strictly, but yeah, and it's fewer than 6 means
Fewer
include
than
5.
itself means less than.
Yeah.
Fewer than itself means less than 6.
Yeah, it's less than 6. It's not less than 5. It's less than 6 one. I thought it's less than 5 written here. That means you don't have to, you have to exclude this.
So can you
No, if
explain
you
this once again? My
exclude, sir,
signal
then it
was
will not
lost.
come, sir.
Okay, I'll explain it again. So see, for the geometric, what generally we do is, okay, so for geometric, what if the probability you have to calculate, if you have to calculate the probability such that x equals to here 6 is been given, right? And probability x greater than 6. So you have to calculate this 2 and subtract it from 1. How will you do that? You can do, because you have been asked to calculate for what? Probability? Sorry, you have to ask calculate probability x such that fewer than 6, right? So what you will do? 1 minus this one, probability of x equals to 6, right? Plus probability such that x greater than 6. Okay? Right?
Yes.
So you have to calculate this. What is this one? This is simply 1 minus p to the power k minus 1 into p. And here what you have to do? You have to do the summation from k plus 1 to infinity. It's the same thing you have to do. It will be a geometric one. The formula for geometric one is a upon 1 minus r. You need to see what is we need to see what is the value of a, the starting point, and what is the r here. The r is 1 minus p, so you'll get something. Okay, whatever you'll get, you add up two things and subtract it from 1, you'll get the value.
So how you calculated for x greater than 6 here? What the sigma sign? What is this done?
Sigma, like for example, for x equals to 6, this is the probability density that generally we calculate for geometric, right? So if you will ask x greater than 6 means what? X greater than 6, we have to do the summation for all the values greater than 6, right? So from 7 to infinity we have to do, because we can get the that 6 number, that the number in the 7th term also and the 8th term also, maybe in the 9th or in the infiniteth term, right? That's why we are doing the summation for all the term.
Yes.
Yeah, so this is what has been done, and and then you can subtract it from 1, or else you can, what you can do, you can just do the summation for all the x equals to 1 to till 5 and get the value. So these are two ways to do this, I guess. Yeah.
And so one more question, sir. Sir, in question number 23.
Question number
23.
Okay. Yeah, so it is a series of 4 matches been played between India and England. Let the x with a random variable represents the absolute difference between the match number of match won by. So India and England played some match. India and England played some match. What is the number of match they have played? They have played 4 matches. Okay, so 4 match series is there. Maybe India can win 1 and England 3. India can win 2 and 2 England. 3-1.
Sir, here I have doubt I have very small doubt here.
Yeah.
So we are getting the answer as 0, 2, 4 as the difference. So
yeah.
I understand for 2 and 4, it is 1 or 3, 3 or 1 or 4 or 0, 0 or 4. But it can't be 2 or 2 because here it is it's saying the match couldn't result in a tie.
Match couldn't relate. Yeah, so match can't be tie. Like out of 4 matches, all the 4 matches will be having some winner and some loser. So the match can't tie means like India just scored 180 run and England also scored 180. So that can't happen. So every time
India won 2 matches. India won 2 matches and England also won 2 matches. Then it results in a tie number.
No, this is not tie. This is like equal in the series. Like
no,
they have
tie is there is no win or lose. It's a draw.
Yeah, tie is means there is no one losing or winning the match.
So sir,
it's not India 1-2
happens, then what will
here India 1-2, England 1-2. It's not a tie. India 1-2 match, England 1-2 match. It's not a tie match.
The match should not be tie, but the series can be.
Okay, I think so. It's clear now. So yeah, we'll move forward now. Is this clear? Right?
Yes, sir. Yes, sir.
Okay.
So in question number 25.
Can we discuss it after the Jacobian?
Yeah. Okay.
Yes, I guess there are too many questions.
Okay, so I'll just open the file that I've shared already with you. So I'm just telling you thrice or fourth time. Just go through all the problems, whatever has been given here. Okay, so from here only we'll see the Jacobian matrix. Okay. So,
sir, I think you have posted this, right?
Yeah, I posted this on the
Where
Discord.
have you posted this?
On the Discord, I have posted this.
Can you, sir,
Okay,
just upload here, sir? Means in the chat.
Where?
In the chat.
Okay. In the chat, we can upload.
Yeah, sir. Please. Then we can download here.
How to upload that in the chat?
So like, just you can
Sir,
upload it
share
on
the
Google
link,
Drive
sir.
and share the link. Because
Yeah, I can share the link now, right?
Yeah, that's the thing. If it is on Google Drive, so.
Yeah, I'll just stop sharing and I'll just share 1 minute. I'll just.
Yeah, sure.
Okay, so I've shared the link. Maybe you can open that. Okay, so you're able to see that, right?
Yes, sir.
Okay, so where was I? Yeah, transform that. I don't know which problem has been discussed there. That's why I'm saying, but the number of deliveries can't be infinity. We should know if the match is ODI or T20. Okay, so I'll just start with the transformation thing. So we'll discuss the Jacobian itself here. Okay, so you can expect some problem, this sort of problems where you have been given the PDF function in the form of xy. Okay, so the random variable will be xy, and then the some transformation will be given there. Like here it has been given u and v, and the transformation will be given like the transformation given is 1/2 x minus y, and v is equals to y. Okay, so there are generally 2-3 steps to calculate the distribution. To calculate the distribution, and you have been asked to calculate the distribution of UV, not the XY, because XY has been given here. You have to calculate the distribution in the form of UV. Okay, distribution with the PDF function for the UV. Okay, so how will you do that? So you can do this if you are able to express this XY in the term of UV. Okay, so what you will do, you just write XY in the form of UV. XY in the form of UV means you just have to write the inverse function of u and v in that form of xy, right? If you are, and then you need to calculate the Jacobian. That means, see, you were having this u equals to 1/2 x minus v, x minus y, and v equals to y. This was the transformation given here. Okay, so how can you write this? Y equals to v you can write, and x you can write. Okay, so then you can calculate the Jacobian. Jacobian, how will you calculate? This is the formula for the Jacobian. So this is the same formula that we are using. So dx upon du, dv upon du, or you can say, you can here again you'll get the symmetric matrix. So dx upon du, or dy upon du, or dx upon dv, or dv upon d. So this, you should be aware of that. So you are having the function xy, first you are differentiating with respect to u, then with respect to v, or again you are differentiating with respect to dy with respect to u and dy with respect to v. Okay, so you'll get the Jacobian function, and the Jacobian will be like this. Okay, so Jacobian can be a function of ub also. Like for example, if I would have written, if in the transformation I would have got y equals to v square, then you would have got the Jacobian in the form of ub also. Okay, so it should be pretty clear in your mind that Jacobian also can be some constant value, but can be some variable also. Okay, for this question, we are getting the constant function, it's fine, but we can get the Jacobian in the form of uv also. Okay.
Yes, sir.
Yeah. So Jacobian you can calculate in this way, and the basic formula how to calculate the transformed random variable is you just have to need to write the same PDF and multiply with the Jacobian, and wherever you are doing the xy, just replace it with the uv. Okay, because you are writing the random variable in the form of, you are writing the probability density function in the form of ub. That's why you'll just replace xy with the form of ub, and just see whatever the domain has been given for xy, just write the same, not the same thing. You need to write, you need to see for which u and v this PDF function has been defined. Okay, like for example, for our first problem, this ub can be written in this form. What we have done, we have just replaced the function xy, we have just replaced the xy with the uv that we have calculated, right? So y equals to v and x equals to 2u plus b. So we have just written the same thing here, and we have got the this random variable in the form of uv. Okay, so and how will you do the for the domain? So for the domain also, like for example, xy was greater than 0, so you'll do the same thing. Xy you already know, so xy, y is v and x is 2u plus b. So you'll write it here, u greater than g, or u plus 2u was greater than 0, so u is greater than minus 2u, so you will be from minus infinity to infinity. So in this way you are able to write the transformed random variable, like the PDF function for the transformed random variable. Okay, you can, like, if you've been, so can somebody tell me what's the marginal distribution of u?
So it will be integrated in terms of u.
So you can integrate. So this function you already have, this is the joint density function. You can integrate it. You are fixing the u value, and you can integrate it the v from minus infinity to infinity, or from 0 to infinity, because the domain for v is 0 greater than 0. Okay, so you can get the marginal density function also. Is this clear to everyone? How will you calculate the Jacobian? How will you calculate the transform random variable? Everything is clear, right?
Yes, sir.
Yes, sir.
Okay, so similarly we have discussed 2-3 problems. We just go through all the 3 or 4 problems. This is sufficient to solve your problem in the exam. Okay, so this will be more than sufficient to solve. Okay, if the marginal is not been calculated, you can calculate, like I told you the procedure to how to calculate the marginal density function. Okay, if you are having doubt, you can
u and v, sir.
What
will they give u and v, sir?
Yeah, transformation they will give you.
So the domain for the second question.
Yeah, second problem.
Yeah, if you just go down a bit, the domain for u and v when you calculate. So will it be u greater than 0 and v greater than minus u by 2?
So here, okay. So you need to solve like this. You can take first 2, 0. So u is greater than 0. Then you can take, I guess, this 2, and then you can take this 2, I guess, to solve the problem, to get the domain of uv.
So is it possible that you can include the marginal which you get for at least one of these, so that we can verify our answers?
Okay, then I'll solve for one problem.
One
maybe
of them
out
at least, so that that's
yeah.
just for verification.
Okay, I'll solve for one. So see, okay, so what they'll ask you, if they can ask you like this also, to calculate the probability density, marginal density, to calculate the PDF of 1/2 x minus y. That means what you have to do, you have to calculate the marginal density of u, right? Is this clear to everyone? If you have been asked to calculate the density, probability density function of half x minus y, then what you will do?
Find the marginal for U.
Yeah, find the marginal density for U.
Okay.
Sir, can you just explain how you calculated the domain for the second problem?
Okay, so for the second problem, see, if I'm having, so what you can do is, you can just take 2 U by 2 greater than 0, okay? And then what is been given? V plus U by 2 greater than U by 2, and then V plus U by 2 less than infinity. So this 3, if you will start solving from here, you'll get the domain for U.
Okay, thank you, sir. Thanks, sir.
Okay, so these are the 4 problems. This should be like, there can be some random, but this 4 problem will suffice you to solve the problems. Okay, so the Jacobian, the transformation is pretty clear. So these are some of the important problems from the 11th week. Okay, so is there any issue in the 11th week? You can ask me. I'll just wait
Sir,
for one.
the Jacobian problem will be like multiple choice question, right?
Yeah, Jacobian will be multiple choice problem.
Sir, is the entire paper solvable within 90 minutes?
What I saw, the paper can be solvable in, I guess, 1 hour itself, because many of the problem like KKT condition has not been there. The problems that generally is difficult to solve, like the SVD problems and all, is like given in such a way that you can solve it in a minute. So
No, sir, not from your point of view, from student's point of view.
From student point of view only, I'm saying. So all the SVD problem has been given in the such a way that you can solve directly with the help of that. It told you to calculate the diagonal matrix, like the singular value matrix first, and from there itself you can see the SVD problem. So the problem has been given in such a way that that the computation is not much. The computation will be only for those problems like in the Lagrange problems. You need to get the x, y, x, 2, 3 values of x you'll get, and then you need to put it and then get the values in minima or maxima, and then decide whether it's a maxima, for which values it's coming to be minima and coming to be maxima. Okay. And everybody knows the equation of the plane, right?
Yes, sir.
Yeah, so equation of the, so if you have been given the equation of the plane in the form of vectors, so don't get confused. How will you write? You should be given in the form of x, y, z only. If you have been given the form of RD, you should be able to know like how to convert that in the form of x, y, z. The plane
Sir,
equation
RD means
it's a simple vector in the form of vector. You can do, no, not vectors. See, if you have been given the form of RD, now what you will do is just multiply this xi plus yz plus zk, okay, to that whatever is given here, the plane. Okay, you'll get in the form of xy. So do the dot product, you'll get in the form of xy. Okay, the plane, and whatever you'll get here, the d, that is the simply the distance of that plane from the origin. Okay.
Yes, sir.
Yeah. So whatever, see. So if this is given R, generally there is, you can just write the R there in the form of this xi plus yj plus zk, and do the dot product with the plane that has been given in the form of xy, I cap, j cap, and k cap, and then you'll get the equation in the form of xyz. From there, you'll be comfortable, I guess, to solve the problem, because all the problem what you have seen here is in the form of xyz. So if this question is given in the form of vector, so don't get like confused with that. Okay, you just have to convert that in the form of xyz and we'll be able to solve. Okay, so this is fine. What else is left? Okay, is there any doubt from 11th week?
11th week, sir. Graded assignment problem number 10, sir.
Okay, graded assignment problem number 10. Okay, 11th week, right? This one.
No, not this one. Just hold on, sir, 1 minute. Not this one.
Okay, so I'll just put it in the chat box again. So which slides you need now? Tell me. I'll just put the SVD slides you need or what?
So problem 5.
Okay, this one.
Yes,
Suppose that the random variable x is uniformly distributed between 0 to 10. Okay, so this is the random variable has been given here. Uniformly distributed. Uniformly distributed, you know, okay, so this is
1 by b minus a, yeah.
Yeah, so this is uniformly distributed from 0 to 10, right? 0 to 10 means the height will be 1 upon 10. Correct?
Yeah.
Now what you have to calculate? Probability such that x plus 10 upon x is greater than equals to or 7, right? Or greater than only. Greater than equals to. So just solve this problem. Solve this x square plus 10 minus 7x equals to greater than 0. X square minus 7x plus 10 greater than 0. So I think so x should be
5 and 2.
5 and 2 is the solution. Okay. So 2 and 5 is the solution. 2 and 5. So what is been asked here? Should be greater than equals to 0. So x minus 5 and x minus 2 should be greater than equals to 0. So if you solve this equation, what are the values of x you are getting? So this is the line. This is 2. This is 5. If you will put any minus infinity here, minus infinity will be positive. Okay. So this you require. This you don't require and this you require. Okay. So from this area you require. And I guess this area you require. So what is the area inside this? This is 0.5 and this is area 0.2. So the probability is how much? 0.7. Is it clear?
Yeah.
Yeah. So, okay. So, yeah. So, yeah, I'll tell you again the 11th week. The one thing is the transformation problem, the Jacobian, okay, marginal, conditional, and the basic properties you should be able to know regarding the probability. And if you are able to solve this problem, you'll be if you are able to know the concept of these problems, you'll be able to solve the problems from the 11th week. Not much difficult problem would be there from the probability. Okay, none of the any difficult formula or anything that you required in the stats 2 or stats 1 will not required here to solve any of the problems. Okay, all the question will be basic basics to solve. Okay, so you'll be able to solve from the 11th week. So
probability, sir, base theorem based question will be there.
Not base theorem, basic probability concept.
Sir, can we expect like in a mock, sir, that discrete random variable and continuous
mock?
random?
I didn't solve. Wait, I'll just check it once. The mock question.
Yes, sir.
The mock. Okay, so first week, okay, you can expect this type of problem. Second also is fine. MS, okay, so this you can find. So yeah, this type of problem you can find. Eigenvector. Okay, this is fine. Okay, so I think so difficulty level is more or less same. This type of problem you won't see. The KKT condition you will not. Yeah, so this is pretty simple, right? The 15th one. You don't require anything, any exhaustive formula to solve this problem. This expectation. You don't require expectation, you already know. Yeah, expectation I forgot. Expectation is important. So if you have been given to calculate the expectation, like for example, you've been given to calculate the expectation of 4x plus 5. The expectation of x has been given as 5. So you can calculate, right? 4 into expectation of x plus 5. You can calculate that, right?
Yes, sir.
4 into 5 plus 5. Similarly, for the variance also you can calculate. Variance is simply ax is what? A square of variance of x. And variance of x will be given, you can calculate. So this is also important. You can just, so this is a bill. I told you the properties. If this is independent, you can directly sum the variance also. For the expectation, you can do for whether it's independent or dependent doesn't matter. Okay.
So will you please share the SVD and that handbook?
Okay. So yeah, so the probability more or less same type of problem there. So not much difficult is there.
Sir, what about 16 and 17, sir? Like that problem can we expect, sir?
60 is pretty simple, right?
Yes, sir.
Yeah, this type of problem will be there from probability. None of the problem is difficult. Okay, so you'll be able to solve all the problems. Okay, so the same in the same whatever the link I've shared, the SPD slide is also updated there. Okay, so you can just take it there.
Sir, that from Berkeley you shared last
Yeah,
time.
I shared in the chat box, right? So in the same file, there's all the files are there. If you
Okay,
need
sir,
anything else, also I'll upload it itself. Okay, if you need, just tell me till the end of the session. I'll just upload the slides.
Okay, sir. Thank you.
Okay, so now we'll move to the next part. That is the last week. That the 12th week.
Sir, SVD is not there in that link, sir.
SPD is not there. Where is that? SPD. I guess I uploaded now. Yeah, so it's fine. So it's uploaded now. So week 12, one thing is like you can go through the tutorial once more. Okay. But the problem I already told you from the week 12.
Sir, that link is only for transformation problems, sir. Only that PDF is open.
Only that PDF is open. Is that?
It will be there in the drive, not in the link.
Yeah, I think you have to provide the access to your directory.
Yeah, I said no. I think so. Just open that. Okay, so 12th week is, yeah, so this is the final week for us. This is the last week. Yeah, so the best part for you is that from the 12th week, most of the concepts are very much theoretical and none of the theoretical question has been asked here. So 12th week, the most important thing from the 12th week is the MLE concept. Okay, and for the MLE concept, you should be able to know for the Poisson distribution, how will you estimate the value of lambda and the exponential and the normal distribution. Okay, this three is important. And the Chebyshev inequality and Markov's inequality. These are the important topics. Okay, from the 12th week. You can go through the tutorial also once. Let's go through all the problems. Okay, I'll just.
This Gaussian mixture will not be there.
So Gaussian mixture is a totally theoretical part. The Gaussian mixture or EM model, expectation maximization model, okay, or the linear transformation. Linear transformation will linear transformation almost same as whatever we have discussed in the 11th week. So here it has been same. Only the different part that has been discussed in 12.1 lecture is what we are taking x1 equals to, like, we are just writing the n number of normal distribution in this form, vector form, right? And for simple transformation, what we are doing, x2 equals to rho z1 plus 1 minus 1 to z2. So we are taking this in this form so that our Jacobian will be a pretty simple one. So Jacobian will be what? Jacobian, I don't know what. This is rho 1 minus 1 minus 2. This type problem, the Jacobian generally you get. So I'll just start with the first topic. The first content is that there. Yeah. In the first lecture, so this simply, it's like theoretical only. The problem that has been there in the practice and graded, please do that once. Or tutorial, you can refer the tutorial to get the more information how to solve this problem if you are not able to solve. Okay, so you can just go through the tutorial once. The basic part behind this is on the same page that we are doing for the transformation. Okay, so like here also we have the n number of standard normal distribution. So how will you write that? If you are writing, this is simply the product of all the product of all the standard normal distribution. Okay, and if you have been given, like for example here the transformation has been given here, x1 equals to z1, so z1 the standard normal distribution, and x2 also has been given in this form. So the transformation has been given in such a way that the computation will be pretty simple. That's why sir has just took this x1 equals to z1 and x2 is in the form of rho z1 plus under root of 1 minus rho square z2. Okay, and if you'll start solving this, you'll get this A, and this is the A inverse. A inverse is generally the Jacobian. So why this is the Jacobian? Because in the same way we were writing the transformation also, we were doing the same thing. We were taking the inverse and then differentiating with respect to whatever the variable we were having, right? So in the transformation, we were having u and v, right? So we were differentiating with respect to vu and v. So here the transformation is in the form of x1 and x2. So we are transforming in the form of x1 and x2 only. So this is the A inverse, this is the Jacobian, we can say, or you can say the determinant of this matrix A inverse. So similarly, if you have to write the PDF function in the form of x1 and x2, so he'll do the same thing. So this all, now it's not important. If you are knowing, it's fine. So this is the same thing he'll do in the end. That in the end we'll get the probability density function, the PDF of in the form of x1 and x2. So we'll see that again we are doing. So this is the Jacobian. The Jacobian is what? The determinant of A inverse that I told you in the starting. This is the A inverse. This is the Jacobian. How generally we get the Jacobian? You already know. We are just differentiating. We are just finding the inverse in the form of the transform thing x1 and x2, and then differentiating with respect to x1 and x2. Okay, we have to just differentiate this with respect to x1 and x2 to get the Jacobian. Okay, so the Jacobian we already know. So what we are doing the same thing. We are just multiplying the PDF function with the Jacobian. So again we are doing the same thing here. We are just multiplying the PDF function that we were already having with the Jacobian, and in the end we will see that this can be written in the form of this also, in the form of normal distribution of x given 0 and x2 given rho x1 with the variance of 1 minus rho square. The same thing here, just plotted. How does it conform? You see, you can see that whenever you are fixing x2 equals to rho x2, this would be a normal distribution. How will you say that this is the normal distribution? See that wherever the line passes this x2 equals to rho x2, so this is that you can see that a bunch of points are there. So in the normal distribution, you already know wherever there is a mean value, there is a bunch of distribution, right? So these are all theoretical. The problems, what can be made has been discussed in the tutorial. You can just watch those tutorials. So there can be 2-3 types of problems that we have already discussed in the tutorials. Not much more than that will be asked in the exam. Okay, the basic concept behind this is pretty given. If you have been asked to calculate Jacobian, and if you have been given the transformation like this, you should be able to calculate just the determinant of A inverse. Okay, is this clear to everyone?
Yes, sir.
So can you come again?
Yeah, so what I was saying, if you have been asked to calculate the Jacobian, and if the transformation has been given like this, you can directly calculate the determinant of A inverse, okay, to get the Jacobian, right? Or you can write this matrix and then calculate the you can just differentiate it with respect to x1 and x2 and then get the Jacobian, right? See, here x1 and x2 has been given. What you have to do now? You have to write z1 and z2 in the form of x1 and x2. Okay, and then differentiate with respect to the differentiate Z1 and Z2 with respect to X1 and X2 to get the Jacobian. This is how we were doing in the starting, right? I told you in the 11th week also, we were differentiating the X with respect to U and V. Is this making sense?
Yes, sir.
Here what you, here also the transformation is given, x2 equals to v, x1 is equal to uv, right? The same thing has been given here. So the transformation is x1 equals to z, x2 equals to this. The transformation has been given. Again, what we are writing here, we are calculating the Jacobian. How generally we are calculating Jacobian? We are writing uv in the form of x, x1 and x2, and then differentiating, right? See, what I did is the first step is express xy in the term of uv. Okay. So here also you have to express z in the form of x. Same thing. Now the domain, okay, that's fine. The calculate the Jacobian. So here to calculate the Jacobian, what we were doing there, we were differentiating with respect to u. We were differentiating the x with respect to u. So there we'll differentiate z with respect to x1 and then z with respect to what? Z1 with respect to x1 and then z2 with respect to x1, then z2 with respect to x1 and z2 with respect to x2. Same thing we'll do in spite of u and v. There it is z1 and z2.
Yeah.
Right. So the same thing has been done here. Here only the thing is xy uv is there. And here it is Z1, Z2, and X1, X2. The transformation is same. You just need to inverse this. After inversing this, calculate the Jacobian. That's it. Is this making sense? Yes. Is this making sense?
Yes, sir.
The same thing is there. So see, should I repeat it or should I write it?
It is clear, sir.
Yes, sir.
Okay. So the Jacobian you can calculate, right? If you have been given the equation, you can calculate the Jacobian. There's no problem in that. 3-4 times I told you, even if you are doing mistake in the exam, I'll kill you. Okay, so this is done. So from 12 point, like from first lecture, so almost everything, like from the diagram also you can see that the same thing has been after the computation. Here just came to this conclusion. Okay, the conclusion was what? So if you are writing the density function, so what you have concluded that the conclusion is the first term you are getting is the normal distribution, standard normal with x1. Okay, so we were having two x1 and x2, right? So the transform thing, so x1 x2 this is a combination of x1 and x2 only, right? The probability density function, it can be written in the form of normal distribution function, x1 given 0 as the mean and 1 as the variance, and the second is one is what, x2 given rho x1 and 1 minus rho square is the variance. Okay, from the, you can see this from the here also. Okay, see, so if we have to write this x1 and x2, the probability density function we were writing, this can be a combination of two normal distribution. One normal distribution is in the form of x1 given 0 as a mean and 1 as the variance. The second one is x2 with given rho x1 is the mean and 1 minus rho square is the what you can say, the variance. Okay, and the same thing we are doing, we are seeing this. Even if I'm fixing the value of x2 equals to rho x1, you can see this wherever the line is passing. So this is a normal distribution, like the yellow one is a normal distribution. The blue one is also a normal distribution. The normal distribution, if you can see this, where the line is passing, that is simply the mean value. At the mean value, all the clustered data are there. You can see this is a, so this is what has been discussed in the lecture. Okay, this picture It's confirming us, okay, this is the PDF function that we are getting, the combination of this two normal distribution. Okay, so this is the simple, like what do you can say, all the theoretical concept has been discussed here. From here, you should be able to calculate the Jacobian, that if is asked, you should be able to calculate. Okay. The second lecture is the estimation of parameter using the MLE, maximum likelihood operation. So likelihood function, you already know how to write the likelihood function. Likelihood function is simply the what do you can say, the proportional to the probability density function at that point. If you are having given 5 points, you can write it, right?
Yes, sir.
See, for example, you can just see this example. This one, where is that one? Okay, so you can see this example. There is a so solve with us. We have discussed one problem. Okay, just practice that problem. So where is that solve with us problem? Okay, this is the solve with us. So this is for the exponential. Similarly, you can do for the Poisson also, and for the normal distribution. Normal distribution is given in the discussed in the tutorial. You can see that. Okay, the exponential I'm telling you here. Okay, see, for example, if you have been given, okay, so this is suppose the lifetime of a light bulb is in the form of exponential distribution with some parameter, lambda parameter, right? So lambda you need to estimate. Okay, so for the exponential, I'll just tell you the basic, how generally you write the exponential function. Can somebody tell me how generally we write the exponential? Lambda e to the power minus lambda x1, right?
Yeah.
Okay, so if this is the data point 1, you can write this likelihood function is proportional to this. So how will you write the likelihood function for x1, x2, x5? You can just multiply all the things. Similarly, till lambda e to the power lambda x5. So lambda to the power 5 into e to the power minus lambda, summation of all the x. Okay. If you will take the log value, log L, you can take the log here also. If you are taking the log, so 5, something log 5 lambda. So no, here should be positive. Okay. Lambda minus lambda summation of xi ln e. Okay. Ln e is what? 1. So equals to 0. If you are differentiating with respect to lambda, you are getting something like this, right? Okay. So if
differentiating,
not now equal to 0, sir.
This it's not. Yeah. Now if we are differentiating, so you'll get 1 upon lambda. Sorry, this is n, right?
This is 5, sir. 5 data point you are taking. Okay.
Yeah, I'm taking 5 data points. If I'm taking n data points, it should be n, right?
Yeah, n yes.
So n upon lambda minus
lambda into summation of
equals to 0. So if you have to n upon lambda equals to summation of xi.
No, there is one lambda, sir.
No, I'm differentiating.
That is differentiating.
Oh, you are already okay.
Okay. So the lambda will be what? N upon summation of xi. So this you should remember for the exponential function. Whatever the data has been given, just do the summation of all the data and divide it. Like just write the number of data points here, you will get the lambda. Similarly, you can do for the Poisson also and for the normal distribution also. Okay, I did it for the exponential. Please do it for the Poisson and normal distribution. Just have to write the log likelihood function. Okay, for the data points, n data points, differentiate it with respect to whatever the parameter you are taking. Like for example, for Poisson, lambda is the parameter. Differentiate with respect to lambda here, and again equate it to 0 to get the estimated value of lambda. Similarly, you can do for the normal distribution. For normal distribution, you should be aware you are having 2 parameters, mu and sigma square. So you'll be given one parameter and then you have to estimate the other one. Okay, so be aware of that. So I guess MLE, you can expect some problems. So please do practice for this exponential, Poisson and normal distribution.
Okay.
Sir, the question will be same like this one, sir, like we saw for exponential. Values will be given directly. No?
Yeah, yeah. Not the same, but yeah, almost.
Yes, sir.
Okay.
So we should practice for normal, exponential, and
Poisson.
Poisson. Yes, sir.
Okay. So now we are into the third lecture. Yeah. So third is totally like EM model, expectation maximization model. So it's not important. It's not like it's important for your future courses, not for the final exam. Okay. The final is what? The final is the Markovs and the Chebyshev. This type of problem, I think so you would have solved at least in the stats 1 and 2 both, right? Here also you have solved 2-3 types of problem. So if you are able to just practice 2-3 problems in the Chebyshev and Markovs, it's more than sufficient. Okay.
Okay.
Yeah. Okay. If you are having any doubt, you can ask me. So
Sir,
I just told you all the important topics. If you are able to practice those topics, I don't think so. Okay, there will be any issue in solving any of the problems from the final.
So just one thing, sir, means finding the eigenvector.
Okay.
If it is particularly 3x3 matrix, I am facing a lot of problems, sir, because it will take a lot of time.
Yeah, it will take a lot of time. Okay, that's fine. That is, I guess I can understand. So, but I think so. I think yeah. So there are some. There must be some problem from the eigenvectors that I told you. Eigenvector and eigenvalue is very important. So you expect some problems. So you can practice 1-2 problems. But that I can assure you, the problems will not be that difficult. You will not get any eigenvalues that equated to 0 or anything repeated sort of thing. So it will be a simple problem that you'll be able to solve. That I can assure you. So there won't be any difficult problem.
Actually, sir, many times there is some difficulty in solving the characteristic equation also, because if we substitute, none of them is satisfying that equal to 0 condition. Then those cases are also there.
Where in the calculating characteristic
equation with from that we calculate eigenvalues, right?
Yeah, eigenvalues
so we substitute 1 minus 1, 2 minus 2, and to find the first factor, na.
Okay.
So
yeah, but
in the exam, sir, it is 3x3 or 2x2.
He's talking about 3x3 only. That's why he need one factor, so that later 2 factor he can get it easily. This is what you are asking, right?
Sir, will they give a matrix and we should find the eigenvectors, sir?
Yeah, from the matrix only you have to find eigenvectors and eigenvalues.
So they'll give the matrix directly, no, sir?
Yeah, they'll give you. Otherwise, how will they give? Like, is there any other method also to ask eigenvector? They'll give you the matrix.
So that matrix will be more than 2x2, right?
I don't know, man.
And
so like, the problem won't be difficult, man. The problem that you have to calculate the eigenvectors, that is not difficult. That you can solve for sure.
Sir, eigenvector means it's multiple choice question.
Yeah, it will be multiple choice. Okay. Is there anything you have to ask regarding the exam? Anything? Yeah, and one more thing from the side, like for example, if you have been asked to calculate, like for example, there is an equation y equals to x plus 10. Okay, and you have been given that x belongs to some gamma function, gamma of some alpha beta. Okay, and then there is a this is the equation that we put to the algorithm, ML algorithm. Okay, and then the exact value y is x plus 7, and then you have to calculate the error. So don't get
afraid of saying this, okay, x is a gamma function, how will you calculate? You have to do the subtraction only, right? So x will get cancelled. This type of problem you can face, like x can be some beta function x. So this type of problem, if you are facing, don't get afraid after seeing just, okay, I'll not be able to solve. So you just have to see that what you have to calculate. You have to calculate which error you have to calculate, okay, and then calculate this. So it will get cancelled.
And sir, otherwise also gamma, beta functions, KML estimators, you won't ask, right?
If they've been, so if they've asked, they'll not ask anything regarding the gamma. Like if you have been given gamma, okay, calculate the what's the mean value. They won't ask this type of problem. But I'm just telling you, if you have been given to calculate in some question, some parts has been given in the form of gamma, but that gamma is redundant. Okay, that is not of use. That's why they have given. Okay, anytime if they have given you also in the problem, that is redundant. Okay, you don't have to use that. If you are like for example here, what is the use of gamma here? Nothing, right? If you have to calculate the error, is there any use? You just have to do the subtraction, right? So it will get cancelled.
Yeah, no. Sir, the error is 3, sir, here.
Yeah.
The error is 3.
If you have to calculate the error, it's directly 3. And then if you have been asked to calculate something else, it's pretty like the part that I was telling is, if they have been given this type of problem, don't get afraid of that. You should just see what you have to calculate. Then okay. If you've been asked to calculate the minimum, like there are 2 types of I guess error. So here, like I'm directly asking the error only. That's why it's 3. If you've been asked to calculate the mean error or something else, then you have to divide it 10 and all. So there are 2-3 types of error. So be aware of that, which is been asked to calculate. Okay. I think so. This is fine. So is there any problem from any of the? Yeah.
Sir, can we expect questions like mock 9 and 10, sir?
Mock 9.
Yes, sir.
Where is the mock question number 9?
Yes, sir. Question number 9 and 10.
9 and 10. Gradient descent algorithm. Okay. Right.
Like that, they are giving the initial point and asking for next 2 points.
Okay, this type of competition won't be there. This is just for the mock, so that you'll be getting well versed. If they're asking also, they'll not ask you anything that needs so much of competition. Okay. So last time also I told you none of the problem would be much. Maybe 1-2 problem out of 20-22 is fine. But most of the problem I can assure you, out of 20-22 questions are there, 15-16 questions are pretty simple. You can just watch and solve. Many of the problem without even pen you can solve.
So how many questions will ask this time?
I guess it should be around 20.
And sir, one small issue is that the quiz 2 marks not revised, sir.
No, it got revised for everyone, I guess. Everyone told me it's revised now. So we have gave the 4, I guess 4 + 4 marks to everyone.
But I didn't get that, sir.
Oh, how is this possible? Everyone got that.
Because initially the mark is showing the same is there. There is no
it
change
got
for
revised for everyone. I see.
No, not for me, sir.
So that question paper was not of 50 marks, that was of 47 marks. So one question has been removed, 3 marks question. And
which one, sir?
That the definiteness, where the matrix was not symmetric, that has been removed. Okay. But for the other 2 problems, that the SVD problem, and there was one more problem, we gave the marks to everyone.
But sir, my marks percentage is same, sir.
Sir, I guess for me also it's same only, sir.
No, for me it is not revised.
Final, whatever the marks has been released, that was the final one. But that came with I only signed off the mark sheet, and I like there was nothing complicated. It's a basic SQL query. I just gave the marks to everyone. And so it's not possible that if like anyone of you didn't got the marks, it's highly impossible. But you can just tell me, like you can just mail me your roll number also. I'll just
yes, sir. I'll mail you my roll number, sir. Just Please cross check, sir.
Yeah, so maybe, so don't worry about that. Just prepare for the exam. Maybe after the exam also I can see that mark. So, okay, so there's nothing worry about that.
Okay.
Sir, can you repeat that R and D part of the plane? I didn't get it.
So R and D part, I was saying for the plane equations. Okay, so like for example, see if the one equation is given in the form of 5x plus 4y plus 6z, okay, then equals to something else that doesn't matter. So if you have been given in the form of, it can be written in the form of r dot of 5i plus 4j plus 6k. So okay, upon the square root of this. So don't get afraid after seeing this. Okay, how will I change this one? So you don't have to do anything. You just have to multiply this. R is what? Xi cap plus yj cap plus zj k cap. Just multiply, just do the dot product. You'll get the exact plane. Okay?
Okay.
You'll get the plane. This is the equation of the plane only. But the plane, the equation of the plane, you are like you are like you are able to solve, or you have seen this problem. You would have seen this also, but from here you'll be pretty easy to solve the problems using the Lagrangian, right? So this is what I was saying. If the problem is given in the form of R and D term, you just convert this in the form of XYZ and then solve the problem. Okay?
Yes, sir.
Yeah, this is what I was saying. So I told you all the important topics and all. So I guess I don't think so there is any topic that I left. So I don't think so there will be any questions that you'll miss out. If you have attempted even the revision session nicely, I don't think so there will be much problem. Whatever I told you, just please practice that and you'll be able to solve. Okay? I guess it's fine. And okay, so all the best for your exam. So
Hello, sir.
You'll rock. Yeah.
Sir, what about week 1 to 4?
What?
Sir, what about week 1 to 4?
I told you from week 1
to 4?
Week 1 to 8, whatever the problem is been asked, all are very simple, very easy. Okay, and the parts will be like I told you, out of 50 marks, 25 to 28 marks will be from week 9 to 12. Okay, and the rest 18 to 20 marks will be from week 1 to 8. Okay, this I told you in the starting itself, like 20%, like 10 marks, and then almost 50 to 60 marks will be from 9 to 12 weeks. Is it clear?
Okay, sir.
Yeah. Anything else anybody has, you can ask, or we'll just go through the important topics. Whatever the time you are left with, one day, I guess tomorrow you have, you can just practice those. You can just go through that and you are ready to go. So all the best, everyone. I think so you'll do well.
Thank you.
Thank you, sir.
Thank you so much.
Thank you, sir.
Okay. Thank you. Thanks.
Thank you, sir.
Yeah. Okay, so I'll close the session. Okay.
Yes, sir. Yes.
Okay. Thanks everyone for joining the session.